Hey guys, tonight we are going to do something a little different. We are going to become time travelers, drifting backwards on the quiet currents of cosmic history. Our destination lies in the deep past, in the moments when the story of our world, the story of life itself, flickered on the edge of extinction. We will visit 5 of these moments, these great endings that were also, paradoxically, the seeds of new beginnings. You and I, we will walk through the ghost of a world that was, stand on the shores of oceans that no longer exist, and feel the phantom chill of an ice age that nearly silenced the planet. This is a journey into the heart of catastrophe, but also into the enduring, almost stubborn nature of life. Now, a small reality check before we depart. If you were to step out of our little time vessel and take a deep breath in any of these lost worlds, well, you wouldn't. The air itself, the very ground beneath your feet, would likely be anathema to your existence. You almost certainly wouldn't survive. But survival isn't our goal tonight. Understanding is. Feeling the immense, slow, and sometimes terrifying pulse of our planet's story is the goal. So, before you get comfortable, take a moment to like the video and subscribe, but only if you genuinely enjoy what I do here. It's always a quiet joy to know that these stories find a home with you. And as you settle in, I would love for you to comment with the city or town you're listening from and what time it is in your corner of the world. It creates this beautiful, invisible map of listeners, all connected by a single story. Let's leave our world behind now, shall we? Let the sound of my voice be your anchor as we let go of the familiar shore of the present. Let's drift back, further and further, past civilizations and ice ages, past the reign of dinosaurs and the first tentative steps of life on land. We are going back to the beginning, to a time before time as we know it, to an ocean without a sky. Imagine a silence so profound it has a physical weight, not the quiet of a forest at midnight, which is filled with the tiny sounds of life, but a geological silence. The only sounds on this infant earth are the hiss of steam from volcanic fissures, the deep, groaning shift of the planet's crust, and the percussive boom of meteorites striking the surface, remnants from the chaotic construction of our solar system. We are standing on the shore of an ocean, but the water is not the familiar, comforting blue we know. It is a strange, murky olive green, perhaps even a shade of brown, choked with dissolved iron. Look up. There is no blue sky, no fluffy white clouds. The heavens are a thick, hazy blanket of orange-pink, a perpetual twilight sky composed not of nitrogen and oxygen, but of carbon dioxide, methane, ammonia, and water vapor. The sun is a pale, distant disk behind this haze, a faint young star that shines with only 70% of its current strength. This is the Earth, some 3.5 billion years ago during the Archean Eon. It is a planet that is both our home and a completely alien world. There is life here, but it is invisible, hidden within the warm, mineral-rich waters. This is the domain of the anaerobes, the first pioneers of biology. The word itself, anaerobe, simply means living without air. For these microscopic beings, the fundamental scientific concept that governs their existence is metabolism without oxygen. They are like tiny chemical engines that have learned to extract energy from the world around them through processes we would find utterly bizarre. Some consume sulfur compounds bubbling up from hydrothermal vents deep on the ocean floor, those volcanic chimneys we call black smokers. In this abyss, far from the sun's weak rays, they perform chemosynthesis, a dark cousin to photosynthesis. They are not pulling energy from light, but from the raw chemical energy of the planet's interior. They are, in a very real sense, eating rocks and volcanic gas. Others consume methane or hydrogen, They have built an entire global ecosystem on chemical pathways that were evolutionary dead ends, pathways that have been relegated to the forgotten corners of our modern world, deep mud, volcanic vents, and perhaps the dark corners of our own digestive tracts. For these organisms, for this first global empire of life, oxygen is not the elixir of life. It is a corrosive, deadly poison. It is a waste product of a chemical reaction they have no use for, a gas that tears apart their delicate cellular machinery. If you were to bubble a stream of pure oxygen into their green iron-rich ocean, it would be an act of chemical warfare on a planetary scale. Their world is perfectly balanced for them. The thick, methane-rich atmosphere that colors the sky, that strange orange, is their shield. This brings us to a fascinating and little-known scientific puzzle known as the faint young sun paradox. Our star was significantly dimmer back then, so by all accounts, the Earth should have been a frozen ball of ice. The water that cradled this early life should have been locked away in a global glacier. Yet we know from the geological record that liquid oceans existed. The solution to the paradox was the atmosphere itself. The vast quantities of greenhouse gases, primarily methane and carbon dioxide, created an atmospheric blanket far more potent than our own. This toxic air was the planet's thermostat, trapping the sun's faint warmth and maintaining the gentle liquid conditions needed for life to begin. This early Earth was a finely tuned system, a world where what we would consider poison was the very thing that made life possible. A world built for anaerobes, and this is where we encounter one of the most profound unanswered mysteries in all of science, a question that is as much philosophical as it is biological. How did all of this begin? What was the spark that ignited non-living chemistry and transformed it into biology? This process, called abiogenesis, is the conceptual bridge between a planet of sterile rocks and chemicals and a planet teeming with reproducing, evolving life. We have compelling ideas, of course. The most prevalent is the primordial soup theory. Imagine this early ocean, not just as water, but as a warm, dilute broth of organic molecules. Amino acids, the building blocks of proteins and nucleotides, the building blocks of genetic material, were being formed through natural processes. Lightning striking the methane and ammonia-rich atmosphere, or perhaps these molecules were delivered to Earth aboard comets and asteroids like cosmic seeds. In this chemical soup, near the intense energy of hydrothermal vents, these simple blocks began linking together, forming more complex chains. This leads to a more specific idea, the RNA world hypothesis. Before the elegant double helix of DNA became the master blueprint for life, its simpler, more versatile cousin, RNA, may have run the show. RNA is a remarkable molecule. It can store information like DNA, but it can also act as an enzyme, a catalyst, to speed up chemical reactions, a job now mostly done by proteins. So, in this early world, you could have a single molecule that was both the blueprint and the construction worker. Imagine a strand of RNA that could, by chance, make a crude copy of itself. This is the whisper of heredity. Now imagine that the copying process isn't perfect. Tiny errors, mutations are introduced. One of these new RNA strands might be slightly better at copying itself, or more stable, or better at grabbing chemical resources from the soup. This new strand would then make more copies of itself than its neighbors. This is the whisper of natural selection. It is not life as we know it, with cells and metabolisms, but it is the first step on that long road. It is a system of information that competes and evolves. But the truth is, we don't really know for sure how it happened. That moment, the precise transition from complex, self-replicating chemistry to something we would all agree is alive, is lost to the deep past. Was it a freak accident? A 1 in a trillion chemical fluke that occurred in one specific tide pool on one specific day, making life in the universe exceedingly rare? Or is life an inevitable emergent property of planetary chemistry? Is it a cosmic imperative, something that will arise anywhere the conditions are right, as common as the formation of stars and planets? Physicists still wonder if the very laws of the universe are somehow fine-tuned to favor the emergence of complexity and, eventually, life. We look at this strange alien world of the Archean, this ocean without a sky, and we are looking at our own origin story. And at its heart is a beautiful, humbling mystery. We are the descendants of a spark we may never fully comprehend. For hundreds of millions of years, this anaerobic world was all there was. It was a stable, quiet, and enduring kingdom. The anaerobes spread across the globe, filling every available niche in their sunless or dimly lit world. They were the undisputed rulers of the planet, their slow, quiet metabolism setting the rhythm of global biogeochemistry. The world was in a state of equilibrium. The iron in the oceans greedily soaked up any trace amounts of reactive chemicals. The methane in the atmosphere kept the planet warm, and life proceeded at a microscopic, unhurried pace. From the outside, it might have seemed that this would be the permanent state of Earth. A quiet, green ocean world, forever dreaming under a hazy orange sky. But evolution is relentless. It is a constant exploration of possibilities, a relentless tinkerer. In the shallower parts of this global ocean, where the faint sunlight could penetrate the murky water, a new kind of microbe was beginning to experiment with a radical new idea. Life had thus far been powered by the planet's internal heat and chemical gradients. It was a life of darkness and geology. But the single greatest source of energy in the solar system, the sun, was largely going untapped. These new organisms, these microscopic revolutionaries, were figuring out a way to harness it directly. They were developing a new kind of chemistry, a new metabolic engine called photosynthesis. They were learning to eat sunlight, and in doing so, they were learning to produce a waste product, a gas that was useless to them, a chemical afterthought to their brilliant new process. A gas that would, over the next few 100 million years, build up slowly, silently, invisibly. It was the deadliest poison the world had ever known. It was oxygen. The stage was being set for the first great apocalypse, not by a rock from the sky, but by life itself. The world was about to take its first breath, and in doing so, it would sentence its first children to death. That silent, deadly poison, the waste product of this new and brilliant form of life, was indeed beginning to accumulate. The revolutionaries, the architects of this coming apocalypse, were a family of bacteria we now call cyanobacteria. You might know them by their more common name, blue-green algae, though they are not algae at all. They were, and still are, masters of survival. Their genius lay in their newfound freedom, while their anaerobic cousins remained tethered to the planet's geology. Huddled around volcanic vents in the deep ocean darkness, the cyanobacteria looked up. They untethered themselves from the Earth and hitched their fate to the star that warmed it. They became the planet's first true farmers, learning to cultivate the boundless energy of sunlight instead of scavenging for chemical scraps in the dark. This was an evolutionary leap of profound significance. They could now live anywhere that the sun's faint rays could reach, in shallow lagoons, in placid tide pools, on the surface of the vast, quiet ocean. They began to spread, slowly, inexorably, across the sunlit portions of the globe, forming thin, greenish films on the water's surface, a living skin on the face of the planet. At the heart of their revolution was a scientific process of almost magical elegance, photosynthesis. It is, in essence, a form of biological alchemy. The ingredients were simple and abundant: water from the ocean, carbon dioxide from the thick atmosphere, and photons of light from the faint young sun. The core of the process takes place within a miraculous little molecule called chlorophyll. Chlorophyll is what gives these bacteria and nearly all plants today their green color. But it is so much more than a pigment. It is a molecular machine, an antenna tuned to the perfect frequency to catch particles of light. Imagine a single photon, a tiny packet of solar energy that has traveled 93 million miles through the void of space, finally arriving at Earth. It plunges through the hazy orange sky and into the green ocean, and just as its journey is about to end, it is caught, perfectly, by a chlorophyll molecule. This captured energy is then used to perform an incredibly difficult chemical task: splitting a molecule of water. This act of splitting water, H2O, was the cyanobacteria's masterstroke. It is a famously stable and stubborn molecule, but the energy of the sun, harnessed by chlorophyll, was enough to break it apart. Once broken, its component parts were reassembled. The hydrogen was used, along with carbon dioxide, to create simple sugars, food for the bacterium, the energy it needed to live, and to build copies of itself. But the oxygen atom, the O in H2O, was left over. It was a remnant, a shard of the broken water molecule that the bacterium had no use for. So it was discarded. This single act of release, repeated trillions upon trillions of times every second across the globe, was the beginning of the end for the old world. For the cyanobacteria, oxygen was nothing more than an exhaust fume, a puff of chemical smoke released into the water. It was the planet's first global-scale pollution, an invisible tide of waste rising from the success of its newest and most innovative inhabitants. How do we know all this? How can we read the story of these microscopic organisms from a distance of billions of years? We can because they were not just organisms, they were builders. They constructed vast, stony cities that have been fossilized in the rock record, providing us with a strange and beautiful little-known fact of our planet's history. These structures are called stromatolites. Imagine a shallow, sunlit lagoon. A mat of cyanobacteria grows on the seabed, a sticky, living carpet. As sediment and minerals drift in the water, they get trapped in this sticky film. To avoid being buried, the bacteria grow upwards, through the sediment, forming a new layer on top, always reaching for the life-giving sun. Over thousands and millions of years, this process of trapping sediment and growing upwards creates layered, mound-like structures of rock. They can look like stony cabbages or domes or even pillars, rising from the ancient sea floor. These stromatolites are the fossilized remains of the world's first reefs, the first large-scale ecosystems built by life. They are the tangible evidence of this burgeoning empire of cyanobacteria. And in a few very special places on Earth, like the hypersaline waters of Shark Bay in Australia, you can still see them today. Living stromatolites, growing layer by layer, just as their ancestors did 3 billion years ago, breathing out the very air that we now breathe. They are living portals to this ancient world, a direct, physical link to the organisms that so profoundly changed our planet. The oxygen these stromatolite cities were producing did not, however, immediately flood the world. The planet had its own defenses, its own ways of absorbing the new poison. For hundreds of millions of years, the Earth acted as a great chemical sponge. The first line of defense was the ocean itself. Remember, the primordial ocean was green because it was filled with dissolved iron, blasted into the water by submarine volcanoes. As the cyanobacteria released their oxygen, this new highly reactive gas immediately found the iron. Oxygen and iron have a powerful affinity for one another, and when they combine, they form iron oxide. You know it by its more common name, rust. For nearly 1 billion years, the planet rusted. As fast as the cyanobacteria could pump oxygen into the water, it was locked away by the iron. turning into microscopic flecks of rust that then rain down through the water column, settling in a thick blanket on the seafloor. This process, the Great Rusting, left behind an incredible legacy. It formed what we now call the banded iron formations, vast deposits of iron ore that are hundreds of meters thick and can stretch for thousands of kilometers. The bands in the rock are thought to represent seasonal or cyclical blooms of cyanobacteria, with layers of iron-rich rust alternating with layers of silica-rich shale. When you look at the steel skeleton of a skyscraper, or the body of a car, or the span of a bridge, you are looking at the fossilized result of this ancient planetary transformation. The backbone of our industrial civilization is built from the rust produced by the world's first major pollution event. But iron wasn't the only oxygen sink. The methane in the atmosphere also reacted with the oxygen, slowly being converted into the less potent greenhouse gas, carbon dioxide. Minerals on the exposed land surfaces weathered and oxidized. The planet was, in every conceivable way, fighting to absorb this new corrosive gas, striving to maintain the anaerobic equilibrium it had known for over 1 billion years. This brings us to a profound scientific mystery that carries with it a deep philosophical question. The earliest chemical signatures of photosynthesis may be as old as 3.5 billion years. Yet the great oxidation event, the moment when oxygen finally overwhelmed the planet's chemical sinks and flooded the atmosphere, didn't occur until about 2.4 billion years ago. That is a delay of more than 1 billion years. 1,000 million years. Why did it take so long? What was happening during this immense quiet interval? Scientists still debate the exact reasons. Perhaps the amount of iron and other reactive minerals was simply so vast that it took 1 billion years of photosynthetic activity to use it all up. Perhaps volcanic activity was particularly high during this period, pumping gases like hydrogen sulfide into the system that immediately consumed any free oxygen. Or maybe the cyanobacteria themselves were evolving, their photosynthetic machinery becoming more efficient over time, slowly ramping up production. The truth is, we don't know for sure what caused this great delay. But the philosophical implication of this time scale is staggering. It suggests that a planet can be undergoing a fundamental, life-altering transformation for a period of time almost too long for us to comprehend. While on the surface, everything appears stable. For 1 billion years, the dominant anaerobic life in the deep oceans would have noticed nothing. Their world was unchanged. The slow, invisible poison was being produced, yes, but it was being safely locked away. This is a powerful lesson in the nature of tipping points. A system, whether it is a planet's climate or an ecosystem, can absorb stress and change for a very, very long time. It can appear to be in a state of perfect balance, even as the pressures mount beneath the surface. And then, one day, the sinks are full. The buffers are exhausted. The system reaches a threshold, and the change that had been building invisibly for eons is suddenly unleashed with what appears to be breathtaking speed. The world had been holding its breath for 1 billion years. Now, as we drift in time towards the end of that long interval, we can feel the shift beginning to happen. The Great Rusting is coming to an end. The oceans have dropped their burden of iron onto the seafloor. The water is beginning to change, to lose its murky green color, and slowly, over millennia, gain the clarity and blueness we know today. The cyanobacteria, unaware of their role as world breakers, continue their work, basking in the sun, splitting water, and releasing their waste. But now, the oxygen they release has nowhere to go. There is no more iron in the water to capture it. It begins to saturate the ocean's surface, and then it begins to leak out. For the first time in the planet's history, free oxygen begins to escape the ocean and enter the atmosphere in massive, world-altering quantities. The slow, invisible poison is now spilling out of its cradle, The hazy orange sky, which has blanketed the planet for its entire existence, is about to be touched by a gas that will tear it apart. For the quiet, ancient kingdom of the anaerobes, the sky is, quite literally, about to fall. The sky did begin to fall, but not in the way one might imagine. There was no thunder, no sudden cataclysm. It was a slow chemical dismantling that stretched across millennia, a silent, invisible reaction happening in the upper reaches of the atmosphere. The oxygen, that hungry reactive gas, having saturated the oceans, was now pouring into the air. It found there an old and familiar atmosphere, a thick, hazy blanket of methane. And the two gases began to react. Oxygen, the great electron thief, tore the methane molecules apart. A molecule of methane, a single carbon atom bonded to 4 hydrogen atoms when met with oxygen, would be transformed. The reaction produced 2 new, far more stable molecules, carbon dioxide and water vapor. One by one, the methane molecules that had warmed the planet for over 1 billion years were being replaced. This had a catastrophic effect on the planet's climate. Methane is a staggeringly potent greenhouse gas, trapping the sun's heat with a ferocity roughly 30 times greater than carbon dioxide. The cyanobacteria's waste product was, in effect, systematically shredding the planet's warm blanket and replacing it with a much thinner, less effective one. It was like swapping a thick woolen duvet for a simple cotton sheet in the middle of a long, cold winter's night. The warmth that had kept the Earth's oceans liquid under a faint young sun was now rapidly bleeding out into space. The planet's thermostat had been broken, and the temperature was beginning to plummet. The Earth was set on an inexorable course towards the longest and most severe ice age in its entire history. But before the cold settled in, the poison took its toll. To understand why oxygen was so deadly, we must understand its fundamental chemical nature. The core scientific concept here is oxidation. We use the word casually, often associating it with rust or the browning of a cut apple. But it is a universal and powerful chemical process. At its heart, oxidation is theft. It is the act of one atom or molecule stealing electrons from another. And free oxygen is one of the most rapacious electron thieves in the known universe. Its atomic structure leaves it with a desperate, greedy hunger for electrons, and it will rip them away from almost any other molecule it encounters. The delicate, intricate molecules that formed the basis of anaerobic life, their cellular walls, their genetic material, their metabolic machinery, had evolved in a world without this threat. They were like a society of gentle beings who had never conceived of theft. Suddenly, their world was flooded with master criminals, molecular bandits that tore their very structures apart, causing irreparable cascading damage. This is what it meant to be poisoned by oxygen. It was a dissolution from within, a molecular disintegration, with the atmospheric blanket in tatters and the poison seeping into every corner of the globe. The Great Freeze began. We call it the Huronian glaciation. It was not a sudden snap, but a slow, creeping cold that descended from the poles. Ice sheets, miles thick, began to grow, reflecting what little sunlight reached the Earth back into space, which, in turn, made the planet even colder. This feedback loop, known as the ice albedo effect, accelerated the cooling. Glaciers, vast rivers of solid ice, began to grind their way from the high latitudes down towards the equator. The oceans, now clearer and bluer than they had ever been, began to freeze. First, a skin of ice on the surface, then a thicker shell, until much of the planet was encased in a prison of ice that may have been a mile deep. This is the snowball Earth hypothesis. For a period lasting as long as 300 million years, our planet may have looked from space like a white, glassy marble, a ghost world locked in a deep and seemingly eternal winter. For the anaerobes, this was an apocalypse on 2 fronts. Those that weren't immediately poisoned by the oxygen now faced a world that was freezing to death. Their warm, shallow lagoons froze solid. The chemical gradients they relied on were disrupted. Their entire world, the stable, gentle, methane-warmed planet that had nurtured them for eons, was being systematically destroyed. The first and greatest mass extinction event was underway. It was a microbial holocaust. Billions of years of evolutionary history were being wiped clean. The death toll is impossible to calculate, but it is estimated that upwards of 99% of all life on Earth perished. The planet fell silent. The global empire of the anaerobes, the life that had conquered the planet in its infancy, was reduced to a handful of desperate survivors. They fled to the only places their two new enemies, ice and oxygen, could not yet reach, deep into the geothermal warmth of the Earth's crust, and into the black, oxygen-starved mud at the bottom of the deepest oceans, huddling near the volcanic vents that still offered a chemical memory of the world that was. And yet, in the midst of this profound destruction, something new and strangely beautiful was being born. As the oxygen scrubbed the methane from the atmosphere, the sky itself changed. The hazy orange-pink sky of the Archean, a permanent, soupy twilight, was gone. In its place, something startling appeared. For the first time in Earth's history, the sky turned blue. The scientific reason is a process called Rayleigh scattering. The shorter, bluer wavelengths of sunlight scatter more easily off the molecules in the atmosphere than the longer, redder wavelengths. With the thick methane haze gone, and the air now dominated by nitrogen and the new oxygen, this effect could finally take hold. Can you imagine it? To be one of the few organisms that survived on the surface, perhaps in a small pocket of geothermally heated water. You would have witnessed the very color of the world change. The sky, which had always been a familiar, comforting orange, would have cleared to reveal a piercing, brilliant, and utterly alien blue. It must have felt like the dawn of a new reality. The very color we associate with clarity, with hope, with life, was born directly from a global catastrophe. The air we now breathe, this specific mixture of nitrogen and life-giving oxygen, was being forged in the crucible of this great dying. This period of global freezing raises a fascinating and as yet unsolved scientific mystery. How did life survive at all? If the entire planet was a solid ball of ice, how did the photosynthetic organisms that produced the oxygen, the cyanobacteria, survive the darkness and cold of their own making? Did the ice not cover the entire globe, leaving a thin band of open, slushy water around the equator? Or did life survive in tiny cryo-oases, small pockets of water kept liquid by hot springs, like warm breaths on a frosted windowpane? Or did all surface life truly perish, with the planet being reseeded millions of years later by the deep Earth survivors that crept back to the surface after the ice finally thawed? The truth is, we are still piecing together the story of this planet's most extreme winter. It is a testament to the sheer tenacity of life that anything at all made it through. And this leads us to a final, more philosophical question, one that sits at the heart of our own existence. Was this apocalypse, this mass poisoning and subsequent deep freeze, a necessary evil? The anaerobic metabolism that powered the first world was slow and inefficient. It produced very little energy. The new metabolism, the one that used oxygen, aerobic respiration, was a firestorm in comparison. It could extract nearly 20 times more energy from the same amount of fuel. This vast surplus of energy was the evolutionary key that would, over the next 2 billion years, unlock all of the complexity we see in the world today. It powered the creation of complex cells, multicellular bodies, nervous systems, brains, and eventually consciousness. We, as complex oxygen-breathing creatures, are the direct descendants of the survivors of this catastrophe. Our lives are powered by the very poison that annihilated the world's first inhabitants. This is a profound and perhaps uncomfortable paradox. Our existence is owed to an event that was, for the life that came before us, a near-total genocide. It forces us to wonder about the fundamental nature of progress and creation. Is large-scale destruction a necessary component of creation? Must old worlds be completely swept away to make room for new ones? After 300 million years, the ice finally did begin to retreat. Volcanoes, which had never stopped rumbling beneath the ice, continued to pump carbon dioxide into the atmosphere. With the oceans frozen over, this carbon dioxide could not be absorbed by the water. It built up in the air for millions of years, slowly fashioning a new, thinner greenhouse blanket until the planet warmed just enough for the thaw to begin. Life, patient and resilient, crept out from its deep shelters and began to repopulate a freshly scoured planet. It was a new world, a world with a blue sky, clear oceans, and an atmosphere filled with a dangerous, energetic, and ultimately life-giving gas. A new set of rules had been written. The first great ending was over, and the stage was being set for the next grand experiment. We must now let go of that new blue-skied world and allow the currents of time to pull us forward. We are leaving the era of microscopic architects and planet shapers behind and jumping across an immense, quiet sea of time. Our next destination is nearly 2 billion years in the future from the end of the Great Oxidation Event. This vast interval of Earth's history is a strange one, often called the boring billion. It is a seemingly quiet and uneventful chapter. The planet had settled into a kind of stable middle age. The skies were blue, the oceans were oxygenated, but life remained stubbornly simple. It was still a world of single-celled organisms. But beneath the quiet surface, a slow, secret revolution was taking place, a masterpiece of cellular engineering that would change the course of evolution forever. This was the birth of the eukaryotic cell. If the simple prokaryotic cells, like the cyanobacteria, were small, efficient, one-room workshops, then the new eukaryotic cell was a sprawling, sophisticated factory, complete with a central office, specialized departments, and an internal power grid. The central office was the nucleus, a secure membrane that protected the precious genetic blueprints of DNA. But the most crucial innovation was the power grid. This came in the form of a tiny organelle called the mitochondrion. The leading theory for its origin, endosymbiosis, is a beautiful story of ancient partnership. A larger host cell, perhaps an early predator, engulfed a smaller oxygen-breathing bacterium. But instead of digesting it, the host cell put it to work. The smaller bacterium, safe inside its host, became a dedicated power plant, using the world's new abundance of oxygen to generate vast amounts of energy for the cell. In return, the host provided protection and raw materials. This partnership was so successful that it became permanent. Nearly every cell in your body, in every animal, plant, and fungus on Earth, contains these mitochondria, the descendants of that ancient oxygen-breathing bacterium. With this new high-energy cellular model, the stage was set for life to get bigger, more complex, and infinitely more creative. And after a billion years of quiet preparation, the curtain rose. Around 541 million years ago, at the beginning of a period we call the Cambrian, something astonishing happened. In a geological blink of an eye, the oceans erupted with a riot of complex animal life. This event, the Cambrian explosion, is one of the most dramatic and mysterious in the entire history of life. For 3 billion years, life had been a single note, a lone instrument playing a simple melody. Then, suddenly, it was as if a full symphony orchestra had been unveiled. In the space of just a few tens of millions of years, nearly every major animal body plan that exists today appeared. It was a frenzy of biological invention, the ancestors of insects, the first creatures with shells, the first faint glimmerings of the vertebrate spine that would eventually lead to us. They all burst onto the scene. Fossils from this period, like those found in the Burgess Shale in Canada, show a world teeming with creatures that seem to come from a bizarre dream. Animals with 5 eyes and a long grasping claw extending from their face. Worms with menacing spines. Creatures that defy our modern classifications. Life was not just evolving. It was experimenting with a wild, unbridled creativity. Our journey tonight takes us to the period that followed this great explosion, the Ordovician, which began roughly 485 million years ago. This was the time when the radical inventions of the Cambrian settled down, diversified, and truly conquered the planet's waters. The world itself was warm and placid. The continents were in an unfamiliar arrangement, with most of the planet's landmass collected into a single supercontinent called Gondwana, located in the southern hemisphere. This created a vast, uninterrupted global ocean, dotted with shallow, sunlit inland seas. Let us sink now beneath the surface of one of these ancient seas. The water is warm and clear, and the world is a garden of unimaginable strangeness and beauty. There are reefs here, but they are not the familiar branching corals of today. These are built by layered stony sponges called stromatoporoids, and by the first, simple horn-shaped corals. They create a complex alien architecture on the seafloor, a perfect backdrop for the teeming life that inhabits it. And what life it is. The seafloor is crawling with trilobites. They are everywhere, the undisputed icons of this age. These armored arthropods, distant relatives of insects and crabs, come in thousands of shapes and sizes. Some are smooth and streamlined, active swimmers in the water column. Others are covered in ornate spines for defense, scuttling between the reef structures. Many are burrowers, plowing through the soft mud in search of food. The water column is patrolled by the era's apex predators, the nautiloids. Imagine a squid-like creature living inside a long, straight, conical shell. These were the giants of their time, some like the species Endocheras, reaching lengths of over 10 meters. They moved by jet propulsion, sucking water in and forcing it out, silently stalking the trilobites and other creatures below. The whole sea is a bustling metropolis. Floating like delicate feathery nets are colonies of tiny animals called graptolites. The seafloor is carpeted with brachiopods, which look like clams, but belong to a completely different lineage, filtering the water for microscopic food. And rising from the seabed, like a petrified forest, are the crinoids, or sea lilies. They are not plants, but animals, related to starfish, with long stalks and feathery arms that gently sift the currents. The Ordovician Sea is a symphony of quiet, constant motion, a world of armor, tentacles, and filter-feeding arms, all playing their part in the first truly complex global ecosystem. Let us look closer at the trilobites, for they hold a particularly strange and wonderful little-known fact. We know from their exquisitely preserved fossils that they had sophisticated eyes, some of the first complex visual organs to evolve. They were compound eyes, like those of a modern fly, made up of many individual lenses. But the material of these lenses is what is so astonishing. Unlike the soft, protein-based lenses of our eyes, many trilobites had lenses made of rock. Each individual lens in their eye was a single, perfectly clear, optically aligned crystal of calcite, the very same mineral that forms limestone and marble. They saw the world through crystalline windows. Some later species, in a feat of engineering that seems almost impossible for blind evolution to produce, developed even more complex lenses. They fused a second layer of a different type of calcite to the first, creating a doublet lens that corrected for the spherical aberration of the light passing through the water. They had, in essence, invented a form of bifocal rock crystal eyewear, 500 million years before humans even existed. It is a humbling reminder that the toolbox of nature is filled with solutions we would consider high technology. This explosion of complexity and innovation during the Cambrian and Ordovician, begs one of science's greatest unsolved mysteries. What caused it? Why, after 3 billion years of quiet simplicity, did life suddenly become so complex, so fast? There is no single easy answer, and scientists still debate the cause of this biological Big Bang. One theory circles back to our old friend, oxygen. Perhaps oxygen levels in the atmosphere and oceans, after rising for so long, finally crossed a critical threshold, providing enough fuel for the high-energy lifestyles of large, active, hunting animals. Another theory points to genetics. It suggests the evolution of a new set of master genes, the HOX genes, which act as architects for the developing embryo, dictating where the head, legs, and tail should go. Once this genetic toolkit was in place, it could be easily modified to produce a huge variety of body plans, unlocking a new world of evolutionary potential. A third popular idea is one of an ecological arms race. The evolution of the first true predator would have set off a cascade. Prey species would be under intense pressure to develop defenses like hard shells and spines. This, in turn, would drive predators to evolve better ways to hunt, like sharper claws and better eyes. This back and forth could have rapidly driven the diversification of life. The true answer is likely a combination of all three, but the question touches on something deeply philosophical about the nature of creation itself. Does change happen slowly, gradually, and predictably? Or does it happen in sudden, unpredictable leaps? The Cambrian explosion suggests that a system can sit dormant with potential for eons, waiting for a single key, be it environmental, genetic, or ecological, to unlock a door into a vast new space of possibility. It hints that the history of life is not a smooth, straight line, but a series of long, quiet moments, punctuated by flashes of brilliant, explosive creativity. Now let us pull our consciousness back from this teeming underwater garden. Let us rise up through the warm water, breaking the surface and hovering in the air. We look out over the vast, sparkling ocean, full of more life than the planet has ever known. And then we turn and we look at the land. We look at the supercontinent of Gondwana. It is a world of utter silence and desolation. There are no trees, no grasses, no flowers. No insects buzz through the air, no birds sing from branches, because there are no branches. The land is a sterile, rocky desert, baked under a harsh, unfiltered sun. There may be some green and brown crusts of bacteria and lichen near the water's edge, but the continents are, for all intents and purposes, completely empty. For all of life's incredible success, for all its diversity and ferocity and beauty, it remains a prisoner of the sea. The world is a paradise, but it is a paradise confined to the water. All of life's complex children are nestled together in a single global cradle. And that cradle, as we will soon see, is about to be violently rocked. Beneath that vibrant, sprawling garden of Ordovician life, an engine of immense and patient power was at work. It is the same engine that operates today, the deep, slow rhythm of our planet's heart, plate tectonics. The core scientific concept that governs this process is the simple yet profound idea that the Earth's crust is not a single solid shell. It is a mosaic, a puzzle of enormous interlocking plates of rock that float upon the hot, semi-molten layer of the mantle beneath. Imagine them as colossal rocky rafts adrift on a sea of viscous stone. Their movement is almost imperceptibly slow, a few centimeters each year, about the same speed at which your fingernails grow. It is a pace so leisurely that it is meaningless on the scale of a single lifetime. But over the course of millions of years, this gentle, inexorable drift can build mountain ranges, tear continents apart, and rearrange the entire face of the planet. It is the slow, silent geology that dictates the stage upon which the fast, noisy drama of biology is performed. During the Ordovician, this slow continental waltz was steering the world towards a precipice. The supercontinent of Gondwana, which comprised the landmasses that would one day become South America, Africa, Australia, Antarctica, and India, was on a steady, deliberate journey southward. Millimeter by millimeter, century by century, this colossal slab of rock was creeping directly over the Earth's south pole. Placing a large contiguous landmass over a pole is one of the surest ways to trigger a global ice age. The reason is a simple matter of thermodynamics. Oceans are excellent at regulating temperature. Currents can transport warm water from the tropics to the poles, preventing the buildup of permanent ice. But land loses heat far more readily. A continent sitting at a pole has no such circulatory system. It simply gets cold. Snow that falls in the winter does not fully melt in the weak summer sun. It accumulates year after year, compacting under its own weight, transforming into the dense blue ice of a glacier. Gondwana's southern journey was the geological trigger, the first domino to fall in a cascade that would lead to the planet's first great biological crisis. As the great ice sheets began to grow on Gondwana, the planet began to cool. The warm tropical seas that had nurtured such an explosion of diversity grew chilly. Species that had evolved in balmy waters found themselves shivering in a world that was becoming increasingly hostile. But the cold itself was not the primary killer. The true devastation came from a far more subtle, yet more profound, consequence of the ice. As more and more of the world's water was drawn from the oceans through evaporation, precipitated as snow over Gondwana, and locked away in these growing glaciers, the global sea level began to fall. It was as if a cosmic hand had reached down and pulled the plug on the planet's bathtub. The drop was staggering, perhaps as much as 100 meters, maybe even more. This was the true killing mechanism of the first pulse of the Ordovician-Silurian extinction. Remember that beautiful, teeming underwater world we just visited? The vast majority of its inhabitants, the trilobites, the brachiopods, the reef builders, all thrived in the shallow sunlit waters of the continental shelves and the vast inland seas that flooded the continents. As the oceans receded, these habitats, the most biologically productive regions on the entire planet, were simply drained. The sprawling, vibrant underwater prairies were left high and dry, exposed to the harsh air. The delicate reef structures, built over millennia by sponges and early corals, were stranded far from the water, becoming lifeless monuments of rock. Entire ecosystems were being erased, not by a sudden violent event, but by the slow, silent retreat of the shoreline. The cradle of life was shrinking, its waters draining away, and countless species were being left stranded on the barren shores of a dying world. It was a mass extinction driven by habitat loss on a planetary scale. While this glaciation, driven by plate tectonics, is the most widely accepted explanation for this catastrophe, some scientists have proposed another, far more dramatic and unsettling possibility. A little-known theory that adds a layer of cosmic vulnerability to the story. This is the gamma-ray burst hypothesis. A gamma-ray burst, or GRB, is the death cry of a truly massive star, many times the size of our sun. As such a star exhausts its fuel, its core collapses in on itself, forming a black hole, while its outer layers are blasted into space in a supernova. In some cases, this collapse produces two incredibly powerful, tightly focused jets of gamma radiation, shooting out from the star's poles at nearly the speed of light. These beams are among the most energetic phenomena in the entire universe. The hypothesis suggests that around 450 million years ago, one of these events occurred in a star perhaps a few thousand light years from Earth, and that our planet, by sheer cosmic bad luck, happened to be directly in the path of one of these beams. The consequences would have been swift and devastating. As the burst of radiation washed over our planet, It would have slammed into the molecules in the upper atmosphere, rapidly destroying the Earth's protective ozone layer. Without the ozone shield, the planet's surface would have been blasted by lethal levels of ultraviolet radiation from our own sun. The microscopic plankton living in the surface waters of the ocean, the very foundation of the entire marine food web, would have been wiped out almost instantly. This alone would have caused the food chain to collapse. Furthermore, the atmospheric chemistry changes initiated by the burst would have created vast quantities of nitrogen dioxide, a brownish gas that would have not only blocked out some of the sun's light, but also acted as a catalyst for rapid global cooling, potentially providing the initial shock needed to kickstart the massive glaciation on Gondwana. We have no direct proof that this happened, only intriguing chemical signatures in the rock record that are consistent with such an event. But it remains a chilling thought that one of the planet's greatest extinctions might have been triggered by the distant echo of a dying star. Whether the cause was the slow grind of geology or a sudden flash of cosmic radiation, this extinction event forces us to confront a deep and mysterious question about the relationship between life and the non-living planet. We often think of life as a tenacious force, adapting and thriving on a passive, rocky stage. But the Ordovician extinction shows us that life is inextricably intertwined with the deep, slow rhythms of the Earth itself. The planet is not a passive stage. It is an active and sometimes ruthless co-star. We think of catastrophes as sudden, violent events. This was a catastrophe that unfolded over the course of 1,000,000 years. How does an ecosystem respond to a crisis that is slower than the lifespan of 1,000 generations? For the trilobites and the brachiopods, the world was not ending with a bang, but with the slow creeping chill of the water and the almost imperceptible retreat of the sea. A crisis so slow they could not possibly have comprehended it. This raises a philosophical question about the nature of our planet. Is it merely a complex system of geological and chemical cycles? Or do these cycles themselves constitute a kind of planetary agency? The rock cycle, the carbon cycle, the water cycle. These are the planet's deep breaths, its slow metabolism. The Ordovician extinction was a biological symptom of a change in the planet's geological breathing pattern. It makes one wonder if these mass extinctions are a flaw in the system, a periodic breakdown, or if they are a fundamental part of it, a violent, unsentimental resetting of the evolutionary clock that clears the board for new forms of life to emerge. The truth is, we do not know. We only know that biology is a passenger on a restless rocky vessel, and that its fate is forever tied to the whims of the deep earth. Let us close this chapter by hovering over this transformed world. The great ice sheets, shimmering and white, now cover a vast portion of the southern hemisphere. The oceans are shrunken and cold. Along the newly exposed coastlines, we can see the pale skeletal remains of the great Ordovician reefs, silent limestone tombstones marking the high water mark of a lost world. The survivors of this first devastating blow, those species lucky enough to live in deeper waters or adaptable enough to withstand the cold, are huddled in the abyss. The vibrant, sunlit garden we so recently admired has been ravaged, replaced by a cold, impoverished silence. The planet is in the grip of a long and bitter winter. But this winter would not last forever. The same geological forces that brought the ice would, in time, take it away. And the thaw, when it came, would bring with it a second and entirely different wave of death. The story of the first of the Big Five extinctions was only half over. The long winter, which had held the planet in its cold grasp for millions of years, could not last forever. The same patient geological engine that had driven the supercontinent of Gondwana onto the South Pole was now, with the same unhurried pace, carrying it away again. Beneath the miles-thick sheets of ice, the planet's inner fire had never dimmed. Volcanoes continued to rumble, venting gases from the deep earth into the atmosphere. Chief among them was carbon dioxide. During the deep freeze, with the oceans largely sealed by ice and biological activity at a low ebb, this carbon dioxide was not being absorbed. It began to accumulate in the atmosphere year after year, century after century, slowly weaving a new greenhouse blanket. A critical threshold was eventually reached. The planet's energy balance tipped, ever so slightly, in favor of warmth. The Great Thaw began. The glaciers, those monuments to a frozen world, began to melt. At first glance, this would seem to be a reprieve, the long-awaited arrival of a planetary spring, a promise of renewal for the life that had clung on in the cold, deep refuges of the ocean. But the Earth's systems are complex and deeply interconnected, and this act of healing would unleash a second, crueler wave of extinction. The core scientific concept that explains this second catastrophe is anoxia, a severe deficiency of oxygen. As the colossal glaciers melted, they released an unimaginable volume of cold, fresh water into the global oceans. This meltwater, being less salty and less dense than the ocean water, did not easily mix. Instead, it spread out across the surface of the seas, forming a vast, stable lid, a stratified layer that acted as a barrier between the ocean and the atmosphere. You can see a similar effect when you pour oil on water. The two liquids remain stubbornly separate. This cold, fresh lid effectively suffocated the oceans. The normal process of oxygenation, where wind and wave action churn the surface and mix oxygen from the air down into the deep, was shut down. The deep ocean, which had become the last refuge for the survivors of the first pulse, was now a death trap. This was a particularly cruel twist of fate. The very species that had been hardy enough to survive the global cooling and the catastrophic loss of their shallow water habitats now found their deep-sea sanctuaries running out of air. To make matters worse, as organic matter from the struggling surface ecosystems sank into these oxygen-starved depths, its decay consumed what little oxygen remained and, in some regions, began to produce toxic hydrogen sulfide. The deep waters became poisonous. As the sea levels rose again, flooding the barren continental shelves, they brought this anoxic, toxic water with them. So even as their old homes were being returned to them by the rising sea, they were uninhabitable, a chemical wasteland. This was the second pulse of the Ordovician-Silurian extinction, a delayed blow that targeted the survivors in their very shelters. It was an extinction by suffocation. When the chaos finally subsided, when the ice was gone and the ocean circulation had stabilized, the world was profoundly changed. The seas, once again warm and high, were now hauntingly empty. In total, it is estimated that this 1-2 punch of glaciation and anoxia wiped out roughly 85% of all marine species. The stunning biodiversity of the Ordovician was shattered. Entire families of trilobites, the once ubiquitous rulers of the seafloor, were gone forever. The diverse communities of brachiopods were decimated. The complex reef systems, the planet's first great biological cities, had crumbled. The silence in the water must have been immense. The ceaseless scuttling and filtering and hunting that had characterized the Ordovician seas was replaced by a quiet stillness. The world had passed through a terrible fever, and now, in its wake, it was left weak, depleted, and ghostly. In the fossil record of the early Silurian period, just after the extinction, we see evidence of a strange and fascinating phenomenon, a little-known fact called the Lilliput effect. Named after the fictional island of tiny people in Gulliver's Travels, it describes the observation that the species that survive and first appear after a mass extinction are often dramatically smaller than their pre-extinction relatives. The surviving lineages of trilobites were, for a time, miniaturized. The brachiopods that repopulated the seafloor were smaller. It was as if the whole world had shrunk. Scientists believe this may have been an adaptive response to the harsh, post-extinction conditions. In a world with a disrupted food chain and low oxygen waters, being small is an advantage. A smaller body requires less food and less oxygen to survive. Smaller organisms also tend to mature faster and produce more offspring, which are valuable traits when life is precarious. In the shadow of a fallen empire, it is not the large, extravagant nobles who are best equipped to survive, but the small, hardy commoners who can make a living from the scraps. For a few million years, life had to think small in order to have a future at all. This raises one of the most fundamental and unresolved mysteries in the study of deep time. Who survives a mass extinction and why? What separates the species that are erased from the book of life from those that are chosen to write the next chapter? It is tempting to think of it as a simple lottery, a matter of being in the right place at the right time. And luck, undoubtedly, plays a huge role. A species' fate could have been sealed simply by living in a region that was hit hardest. But scientists believe there are also traits that can tip the odds. One of the most important is the difference between being a specialist and being a generalist. Specialist species, those that are exquisitely adapted to a very narrow set of environmental conditions, a particular temperature, a specific food source, a certain type of habitat, were extremely vulnerable. When their specific world disappeared, they had no alternative and vanished with it. Generalist species, however, those that could tolerate a wide range of temperatures or eat a variety of different foods, had a much better chance. They were the opportunists, the survivors who could make a living in a chaotic, broken world. This forces us to reconsider what we mean by survival of the fittest. The phrase often conjures images of the strongest predator or the fastest prey. But in the context of a mass extinction, fitness takes on a new meaning. It is not necessarily about being perfectly adapted to the world as it is. In fact, being too perfectly adapted can be a fatal weakness. True fitness on a geologically active and unstable planet may be more about resilience, flexibility, and the ability to endure when the entire rulebook of your existence is torn up. It is the fitness of the humble generalist, not the magnificent specialist. It is the ability to survive not just the good times, but the complete and utter collapse of the world you knew. The silence that followed the thaw did not last forever. An empty world is a world of immense opportunity. The great dying had wiped the slate clean. The dominant incumbent species that had monopolized resources for millions of years were gone, leaving a vast number of vacant ecological niches. For the small hardy survivors, the world was a wide open frontier. With little competition, they were free to experiment, to diversify, to evolve into new forms to fill the empty roles. The recovery was slow, taking millions of years, but it was relentless. The reefs began to grow again, this time constructed by new orders of corals that had weathered the storm. The surviving trilobites and brachiopods began to diversify again. And in this new, less crowded world, a group of animals that had been relatively minor players in the Ordovician seas found their moment. The fish, particularly the jawed fish, began a period of explosive evolution that would, in the next geological period, see them become the new rulers of the oceans. Life, having endured its first great trial by ice and suffocation, was not just healing, it was innovating. It was laying the foundations for its next, and perhaps most audacious adventure, the conquest of the vast, silent, and empty lands. The world after the great Ordovician dying was a world of quiet opportunity. The period that followed, the Silurian, was a time of planetary healing. Over millions of years, the vacant ecological roles were filled by new and innovative forms of life. The reefs, once crumbled and silent, began to grow again, this time dominated by new families of corals and sponges that had weathered the long winter. But the most significant development was happening in the water column. The survivors of a humble group of vertebrates the fish, had been given a world with few competitors and even fewer predators. And in this new freedom, they underwent a revolutionary change, the evolution of jaws. This was a pivotal moment in the history of life. The jaw was a staggering predatory advantage, and it set the stage for vertebrates to rise from a minor group of mudgrubbers to the rulers of the seas. As the Silurian gave way to the Devonian period, some 419 million years ago, the planet was warm, the seas were high, and life in the oceans was not just recovering, it was entering a golden age. This was the age of fishes. To swim in a Devonian sea would be to witness a breathtaking display of vertebrate diversity. There were still the ancient, jawless fish, remnants of an older world, armored and slow filtering sediment from the seafloor. The first cartilaginous fish, the ancestors of modern sharks and rays, were slicing through the water, sleek and efficient new hunters. And the bony fish, the group to which most modern fish, and even we ourselves belong, had exploded into two great dynasties. There were the ray-finned fish, whose descendants would come to dominate the oceans of the future. And there were the lobe-finned fish, a group of particular importance to our own story. They possessed fleshy, lobe-like fins, supported by bones that were homologous to the bones in our own arms and legs. They were carrying within them the anatomical potential for a life beyond the water. But the undisputed kings of the Devonian seas were a now extinct class of fish that represent a strange and terrifying little-known fact of our planet's past. They were the placoderms, the armored fish. And their most formidable representative was a creature called Dunkleosteus. Imagine a fish the size of a modern great white shark, but instead of skin and teeth, the front third of its body was encased in thick, bony plates of armor, like a living submarine. It had no teeth in the way we understand them. Instead, the bony plates of its jaw were honed into two massive guillotine-like blades. As it closed its mouth, these bony shears would slide past one another, a self-sharpening mechanism of terrifying efficiency. The force of its bite was one of the most powerful in the history of life, capable of snapping other armored fish in half. The Dunkleosteus and its placoderm relatives were the apex predators, the tyrants of their age, a perfect expression of life's predatory arms race. But for all the drama and innovation happening in the water, the most radical revolution of the Devonian was taking place on the silent, empty continents. For billions of years, the land had been a sterile desert of rock and dust. Now, for the first time, a green tide was beginning to creep ashore. The conquest of the land was perhaps the greatest challenge life had ever faced, and it required a whole new suite of biological engineering to overcome. The core scientific concept here is the immense difficulty of leaving the supportive embrace of the water. On land, a whole new set of physical laws asserted their dominance. There was the problem of gravity. In water, buoyancy does all the work, but on land, an organism needs structural support to avoid collapsing into a heap. The solution was a remarkable polymer called lignin, the substance that makes wood woody. Lignin is a sort of natural plastic, a rigid, reinforcing material that allowed plants to build strong stems and eventually towering trunks to defy gravity and reach for the sunlight. Then there was the problem of desiccation. Life is fundamentally a watery process, and the dry air of the land is relentless in trying to pull that water away. The solution was a waxy coating called a cuticle, a thin, waterproof layer that sealed the plant and prevented it from drying out, like a living form of plastic wrap. But this created another problem: how to breathe. Sealing yourself off means you cannot exchange gases with the atmosphere, so plants evolved stomata, tiny microscopic pores on the surface of their leaves that they could open and close, allowing them to breathe in carbon dioxide and breathe out oxygen while minimizing water loss. And finally, there was the problem of sustenance. In the ocean, An organism is bathed in a soup of nutrients, but on land, the water and minerals are locked away beneath the ground. The solution was the evolution of roots, specialized structures that could anchor the plant and probe deep into the ground, drawing up the water and nutrients it needed to survive. This suite of innovations allowed for an explosion of plant life. The first pioneers, appearing in the Silurian and early Devonian, were small and humble, little green stems like Cooksonia, growing only a few centimeters tall in the damp soils near the water's edge. But by the late Devonian, these humble beginnings had given rise to the world's first forests. To walk in one of these forests would be an alien experience. The air is thick, humid, and still. There are no flowers, as they have not yet been invented. There is no birdsong, no buzzing of insects in the air, only the gentle rustle of the wind through the strange foliage. The trees themselves are bizarre. There are the lycopod trees, with bark that has a strange, scaly, diamond-like pattern. And towering above them all is a tree called Archaeopteris. It is not related to modern pine trees, but it was the first plant to combine a strong, woody trunk with large, fern-like leaves. It was, in essence, the blueprint for a modern tree. This was a world of deep, silent, primeval green, populated only by the scuttling of the first land animals, millipedes, mites, and scorpion-like arachnids, making their living in the new damp leaf litter on the forest floor. This brings us to a profound and often overlooked mystery. In what did these first forests grow? The land was bare rock? The answer is that the plants, in a beautiful act of planetary co-creation, engineered their own environment. The development of soil is a story of the intimate partnership between life and geology. Soil is not just dirt. It is a living, breathing matrix of weathered rock and organic matter. The very first plants would have clung to the bare rock, and their primitive root-like structures would have secreted acids, chemically breaking down the rock surface and releasing its minerals. When these plants died, their bodies would decompose, mixing this organic matter with the rock dust, creating the first thin, patchy layer of true soil. This created a powerful feedback loop. This new soil allowed slightly larger plants to grow. These larger plants had deeper, more powerful roots, which broke up the rock more aggressively, creating deeper soil. This deeper soil then allowed for even larger plants, the first trees. The trees would then shed leaves and branches, contributing a massive amount of organic matter to the forest floor, creating a rich, thick, and fertile layer of topsoil. This raises a deep philosophical question about the nature of life on a planet. We tend to think of evolution as a process of life adapting to a pre-existing, passive environment. But the creation of soil shows us that life is also an active geological force. It doesn't just inhabit a world, it helps to create it. Are organisms merely tenants on a rocky ball? Or is the planet as we know it, with its rich soils, its specific atmospheric composition, its regulated climates, an emergent property of life itself? The first forests suggest the latter. They did not simply find a welcoming home on the land. In a very real sense, they took a sterile, rocky planet and transformed it into a living green world. They made the land. This incredible success story, this greening of the continents, was a revolutionary triumph for life. But biological innovations on a planetary scale are never without consequences. Remember the cyanobacteria, whose brilliant invention of photosynthesis inadvertently poisoned the world for its earlier inhabitants. Now, this new and radical invention, the forest, with its deep digging roots and its constant shedding of organic material, was beginning to have an unforeseen and dramatic impact on the chemistry of the entire planet. The beautiful, silent, green conquest of the land was, without any intention, sowing the seeds of the world's next great dying. A world that had found a new, vibrant balance was once again about to be tipped into chaos, not by a force from without, but by the runaway success of life itself. that triumphant greening of the continents, that quiet, radical conquest, carried within its success a hidden and terrible irony. The invention of the deep, powerful root system was a masterpiece of evolutionary engineering, the key that unlocked the sterile continents. But this new biological technology, in its relentless success, would become the trigger for the planet's next great dying. The roots that held the first trees to the sky would, indirectly, poison the oceans and suffocate the life within them. The story of the late Devonian extinction is a profound and humbling lesson in the law of unintended consequences, a story of how a solution to one problem can create a catastrophe on a scale that is almost impossible to imagine. The mechanism began with the very soil we spoke of, the great collaborative project between plants and rock. As the powerful root systems of trees like Archaeopteris plunged deeper into the ground than life had ever gone before, they acted as powerful chemical and physical weathering agents. They tore rocks apart, and the symbiotic fungi that lived on their roots secreted powerful acids, dissolving minerals that had been locked away in solid form for hundreds of millions of years. This process liberated a torrent of nutrients, especially phosphorus, into this newly created soil. And then the rain came. Rain fell on these first forests, percolated through the new nutrient-rich soil, and washed these minerals into streams and rivers. For the first time, the continents had developed a planetary-scale plumbing system, a network of watersheds that collected this new terrestrial bounty and funneled it relentlessly into the shallow seas and the great global ocean. The land, for the first time in its history, was beginning to actively fertilize the sea. This is the core scientific concept behind the extinction, a process called eutrophication. It is a phenomenon we are unfortunately very familiar with in our modern world. When fertilizer from agricultural fields runs off into a lake or a coastal bay, it causes a massive, uncontrolled bloom of algae. The ancient Devonian world was about to experience this on a global scale. The oceans of the time, while teeming with life, were actually relatively nutrient poor. Their ecosystems were balanced for scarcity. Suddenly, they were being flooded with a feast. This massive influx of phosphorus and other minerals from the land was like pouring fertilizer into the entire ocean at once. The effect was immediate and dramatic. The microscopic photosynthetic life in the surface waters, the phytoplankton and algae, underwent a population explosion. The surface of the global ocean would have turned into a thick, green sludgy soup, a planetary-scale algal bloom. This great algal bloom was the first step in the chain of destruction. This thick surface layer of life would have blocked sunlight from penetrating into the deeper waters, killing off the photosynthetic organisms that lived below, including the great Devonian reefs, which were already struggling with the changing conditions. But the true killing mechanism was yet to come. The algae and plankton in this surface bloom had very short lifespans. As they died, they sank, creating a constant, thick, blizzard-like rain of organic matter, a marine snow of unimaginable density, falling from the sunlit surface into the dark, deep waters below. This sudden, massive glut of food was a bonanza for the aerobic bacteria that lived in the deep ocean, the decomposers whose role is to break down dead organic matter using oxygen. Their populations exploded in response to this endless feast. Imagine a small fire in a large sealed room. Now imagine someone begins pumping fine, flammable dust into that room. The fire will roar, growing larger and hotter as it consumes the new fuel. But in doing so, it will also consume the oxygen in the room with ferocious speed. The decomposing bacteria were this fire, and as they feasted on the sinking algae, they consumed the dissolved oxygen from the deep water faster than it could be replenished from the surface. The result was the onset of global oceanic anoxia. The deep waters of the planet, home to countless fish, trilobites, sponges, and other bottom dwellers, were transformed into vast, suffocating dead zones. This anoxic event, known to geologists as the Kellwasser event, was one of the primary pulses of the late Devonian extinction. The creatures that lived in the deep, unable to escape to the crowded, chaotic surface, were simply asphyxiated. Their world ran out of air. How can we be so sure that this is what happened? Because the planet kept a detailed diary of this catastrophe, written in stone. This brings us to a remarkable and little-known scientific fact that connects this ancient apocalypse directly to our modern world. All over the globe, geological formations from the late Devonian period contain thick, distinctive layers of black shale. In a normal, healthy ocean, when organic matter sinks, it is almost entirely consumed by bacteria and scavengers. Very little of it is left to be buried in the sediment. But in an anoxic ocean, there are no oxygen-breathing bacteria or scavengers in the deep. The blizzard of dead algae that sinks to the bottom is not consumed. It simply accumulates on the seafloor, forming a thick, black, organic-rich ooze, which, over millions of years, is compressed by the weight of the sediments above it and cooked by the Earth's heat into black shale rock. These rocks are, in effect, the fossilized remains of that great algal bloom and the anoxic ocean it created. And here is the final irony. These Devonian black shales, such as the famous Marcellus Shale in North America, are some of the world's richest sources of oil and natural gas. When we drill for fossil fuels, we are often tapping into these 370-million-year-old oceanic graveyards. We are extracting the concentrated fossilized energy of this ancient, suffocating bloom and burning it to power our civilization. An apocalypse of the deep past is fueling the engine of our modern world. This raises a deeper mystery, however. The late Devonian extinction was not a single swift event. It was a long, drawn-out crisis, a series of extinction pulses spread out over some 25 million years. The Kellwasser event was perhaps the most severe, but it was not the only one. What made this period so unstable? The truth is, the Earth's systems are incredibly complex, and the success of the forests likely had multiple overlapping effects. While they were fertilizing the oceans, they were also changing the atmosphere. This massive increase in global photosynthesis would have drawn huge amounts of carbon dioxide out of the air. This, in turn, would have weakened the greenhouse effect, potentially leading to periods of global cooling and even glaciation, a smaller, less severe echo of the Great Ordovician Ice Age. The exact interplay of these mechanisms, ocean anoxia, global cooling, sea level changes, is still a topic of intense scientific research. It forces us to confront a philosophical question about the nature of change. The forest was a solution, a brilliant adaptation. But its success created a cascade of new problems, a series of dangerous feedback loops that destabilized the entire planetary system. This pattern feels eerily familiar. Humanity's own technological solutions, agriculture, industry, medicine, have solved many problems of survival and allowed our population to flourish. But the runaway success of these technologies is now destabilizing the global climate through the very same mechanism. A change in atmospheric carbon dioxide. The late Devonian extinction serves as a humbling deep time parable. It is a stark reminder that no innovation, not even one as seemingly natural and positive as a forest, exists in isolation. It is a warning that runaway success can be its own gravedigger, a cautionary tale that the systems that support life are complex, and that tipping them out of balance can have catastrophic consequences that unfold over millions of years. After the long crisis finally passed, the world was once again a quieter, emptier place. The magnificent and bizarre Devonian reefs, constructed by massive tabulate and rugose corals, were gone, never to recover. The placoderms, the armored tyrants of the seas like Dunkleosteus, had vanished from the face of the earth forever. Their reign was over. Many of the remaining families of trilobites had also perished. The age of fishes had come to a bloody, suffocating end. But the throne room of the vertebrate kingdom was now empty, and two groups of survivors were waiting in the wings. The sleek and adaptable sharks and their cartilaginous relatives, and the incredibly diverse bony fishes, had weathered the storm. And on the shores of the continents, another group of survivors, the very first four-limbed vertebrates, the tetrapods, our own distant ancestors who had just begun to haul themselves out of the water, had just passed through their first great planetary filter. The world was broken, but for these few, the future was an open book. It is one thing to contemplate an apocalypse that arrives in a flash of fire from the sky, a single, terrible day that ends an era. It is another thing entirely to imagine a world that is born into a crisis, that lives its entire life in a state of flux, and that dies without ever knowing a moment of true, lasting peace. The late Devonian extinction was not a sudden event. It was not a swift, clean blow. It was a long, drawn-out, and messy affair, a period of planetary instability that lasted for some 25 million years. It was an endless, lingering twilight. Generations of creatures were born, lived, and died under a sky of constant, low-grade threat. The rules of survival were in a perpetual state of revision. An ecosystem might begin to recover in a shallow sea for 100,000 years, only for the ocean chemistry to shift again, wiping the slate clean. It was a world living through a chronic illness, a planetary fever that refused to break, with moments of seeming recovery followed by another debilitating relapse. To understand the peculiar, cruel nature of this long dying, it helps to understand a core scientific concept about how extinctions work. Scientists often differentiate between two types of extinction events, a press and a pulse. A pulse extinction is caused by a sudden, catastrophic shock. An asteroid impact is the classic example. It is a terrible, violent event, but it is short-lived. The immediate crisis is over quickly, and for the survivors, the work of rebuilding can begin in a world free from the initial threat. A press extinction, on the other hand, is caused by a long-term, sustained environmental stress. The pressure is relentless. The conditions that cause the extinction do not go away. This could be a sustained period of volcanic eruptions, poisoning the atmosphere, or a gradual but irreversible change in the climate. A press extinction grinds life down, offering no reprieve, no chance for recovery, because the fundamental environment has become hostile. The late Devonian extinction was a devastating combination of both. The great biological innovation of the forests acted as the long-term press. The constant, unrelenting flood of nutrients into the oceans was a pressure that never ceased for millions of years. This press continually weakened the world's marine ecosystems, keeping them in a fragile, vulnerable state. And within this long period of pressure, the world was struck by a series of catastrophic pulses. The Kellwasser event, with its massive algal bloom and subsequent anoxia, was one such pulse. The world would be pushed to the brink, and then the system would partially recover, only for another pulse to strike a few million years later, kicking the legs out from under the ecosystem once again. This combination of a long-term press and repeated short-term pulses is exceptionally lethal. It is a form of planetary torture, preventing the system from ever finding a new stable equilibrium. Just when it seemed the long twilight might finally be ending, as the Devonian period drew to its close, one last pulse struck. This final convulsive shudder is a little-known event called the Hagenberg event. It was a complex crisis involving a sudden and rapid drop in sea level, suggesting a brief but intense period of glaciation, followed by a rapid rise in sea level as the ice melted. This flooding of the continents with meltwater triggered yet another widespread anoxic event. But this crisis seems to have had a particularly mysterious and devastating effect on the newest and perhaps most important evolutionary innovation of the time, the first four-limbed vertebrates, the tetrapods. In the very late Devonian, we find the fossils of creatures like Ichthyostega and Acanthostega, pioneers with legs and fingers and toes, our own distant ancestors. They were living in freshwater swamps and estuaries, a crucial link between the world of fish and the world of land animals. And then, at the Hagenberg event, they seem to vanish. This disappearance marks the beginning of one of the most enigmatic chapters in the history of life, a 15 million year long blank page in the fossil record known as Roemer's Gap. For 15 million years at the start of the next geological period, the Carboniferous, we find almost no vertebrate fossils at all. It is as if the great project of conquering the land, which had just begun, was almost extinguished in its cradle. What happened during this gap? Did the Hagenberg crisis nearly wipe out our ancestors, leaving only a few ghost lineages to struggle for survival in environments where fossils could not form? Did the atmospheric oxygen levels plummet, making life difficult for air-breathing animals? We do not know. Roemer's Gap is a silent, shadowy interval in our own deep history, a powerful reminder that the Devonian crisis was a complex, multifaceted affair that continued to claim victims right up to the very end. This prolonged, stuttering nature of the extinction is its deepest mystery. Why did the Earth's systems not find a new balance more quickly? Why did the planet remain in this unstable, sickly state for 25 million years? The answer seems to lie in the mind-bending complexity of the planetary system itself. Imagine an intricate clockwork machine with thousands of interconnected gears. A pulse extinction is like hitting the machine with a hammer. It breaks and it stops. A press extinction is more like slowly pouring sand into the gears. The machine doesn't just stop. It grinds, it shudders, it runs erratically. Some gears might seize up, while others spin faster for a time. The entire mechanism becomes unpredictable. This is what was happening to the Devonian world. The forests were changing the soil. The soil was changing the rivers. The rivers were changing the oceans. The oceans were changing the atmosphere. The atmosphere was changing the climate. And the climate, in turn, was affecting the growth of the forests. It was a tangled web of feedback loops, a cascade of consequences that could not be undone. This raises a poignant philosophical question. What does it mean for a world to be sick? We tend to think in binary terms. A species is either alive or it is extinct. An ecosystem is either healthy or it has collapsed. The late Devonian suggests a third state is possible, a state of chronic systemic illness, a lingering twilight where the world is neither truly dead nor fully alive, but trapped in a painful, unstable state of unraveling. It challenges our desire for neat, simple narratives of cause and effect. The story of this extinction is not a simple story. It is a story about the profound difficulty of predicting the consequences of any new powerful innovation. It is a story that suggests that perhaps the normal state of a complex system is not one of perfect, placid balance, but a constant, dynamic, and sometimes dangerous dance on the very edge of chaos. But even a twilight that lasts for 25 million years must eventually end. The fever did, at last, break. The Earth's systems slowly, painstakingly, found a new equilibrium. The carbon cycle adjusted to the presence of vast forests. The survivors of the Hagenberg event, the mysterious creatures that weathered the storm of Roemer's Gap, did eventually re-emerge. They stepped out of the shadows and into a new world, the Carboniferous period. This new era would be a strange and steamy one, a world of vast, continent-spanning coal swamps, a world where the air was thick with oxygen, allowing insects to grow to monstrous sizes. It was a world that would be built by the descendants of the very plants that had so nearly broken the planet. The long, slow unraveling was over. The slate had been wiped clean once more, and life, tenacious and resilient, was ready to begin its next great chapter. But written in the black shales and the empty reefs of the Devonian, the memory of that long twilight remains. A permanent, cautionary tale of the fragility of even the most bountiful worlds. The long Devonian twilight eventually gave way to a strange and luxuriant dawn, the Carboniferous period. The survivors of the Great Dying emerged into a world remade. The new forests, now a permanent feature of the continents, drove a profound change in the atmosphere. With so much plant life and vast, swampy forests covering much of the globe, the process of photosynthesis was working in overdrive. So much vegetation was growing and dying that it was often buried before it could fully decompose, forming the immense deposits of peat that would, under pressure and time, become the coal seams that give this period its name. All this photosynthetic activity pumped the atmosphere full of oxygen, with levels climbing to perhaps 35%, far higher than the 21% we enjoy today. This oxygen-rich air had a dramatic effect on terrestrial life, particularly the insects and other arthropods. With their simple respiratory systems supercharged by the dense air, they grew to monstrous sizes. Imagine dragonflies with the wingspan of a modern seagull, or millipedes 2 meters long, scuttling through the damp undergrowth. It was a humid, hazy, super-oxygenated world of giants. But for all their size, the arthropods were not the masters of this new world. The vertebrates, our own ancestors, were making a crucial evolutionary breakthrough that would finally sever their dependence on the water and grant them dominion over the dry land. This was the invention of the amniotic egg, a core scientific concept that stands as one of the most important innovations in the history of life. The amphibians that had first crawled from the water were still shackled to it, forced to return to ponds and swamps to lay their small gelatinous eggs. The amniotic egg changed everything. It was, in essence, a private, portable ocean for an embryo. A tough, leathery or hard shell provided physical protection and prevented the egg from drying out. Inside, a series of remarkable membranes managed the embryo's life support. The amnion was a fluid-filled sac that kept the embryo moist and cushioned, its own personal pond. The yolk sac provided a rich supply of food, and the allantois acted as a storage container for waste products. This was a self-contained world, a biological spaceship that allowed vertebrates to reproduce far from any body of water. With this invention, they were finally free to conquer the continents. This freedom led to a great evolutionary split. One branch, the sauropsids, would eventually give rise to the reptiles, dinosaurs, and birds. The other, our own branch, was the synapsids. As this biological revolution was unfolding, the planet itself was undergoing a profound geological transformation. The slow dance of plate tectonics that had been proceeding for hundreds of millions of years was reaching its grand finale. The great southern supercontinent of Gondwana drifted north, colliding with the northern continents of Laurasia. This slow-motion collision, a crumpling of crustal plates over millions of years, forged mighty mountain ranges, including the Appalachians of North America. When the dust settled, for the first time since the ancient days of Rodinia, more than 1 billion years earlier, nearly all of the world's landmass was fused together into a single colossal supercontinent. We call it Pangaea. It stretched from the South Pole to the North Pole, a single immense C-shaped continent surrounded by a single immense global ocean. The formation of Pangaea had a dramatic effect on the world's climate. A unified landmass creates a world of extremes. The vast interior of the continent, thousands of kilometers from the moderating influence of the sea, became incredibly arid, forming one of the largest deserts the world has ever known. The coastlines, meanwhile, were battered by powerful seasonal mega monsoons. The climate became drier, harsher, and more seasonal than the placid, humid world of the Carboniferous. The great coal swamps retreated, and a new kind of vegetation came to dominate the land. Hardier, more drought-resistant plants like the conifers, the ancestors of our modern pine and fir trees. This was the world of the Permian period, a world of deserts and hardy forests, a world before the dinosaurs. And this world, in a little-known fact that overturns many of our childhood preconceptions, did not belong to the reptiles. It belonged to our own distant relatives, the synapsids. For the entire duration of the Permian, they were the dominant terrestrial vertebrates on the planet. In the early Permian, the most famous of these were creatures like Dimetrodon. You have almost certainly seen pictures of this animal, a large carnivorous creature with a magnificent sail of skin supported by long spines growing from its back. It is almost universally mistaken for a dinosaur. But it was not a dinosaur. It was a synapsid, which means it was on the evolutionary line that leads to mammals. Dimetrodon was more closely related to you and me than it was to a stegosaurus or a triceratops. The sail on its back was likely used to regulate its body temperature, absorbing the sun's heat in the cool morning and radiating it away in the hot afternoon. As the Permian wore on, these early synapsids gave way to a more advanced group called the therapsids, which were becoming increasingly and uncannily mammal-like. There were large lumbering herbivores like Moschops, with its ridiculously thick skull. And there were new apex predators. The top carnivores of the late Permian were the Gorgonopsians, fearsome creatures that truly blur the line between reptile and mammal. Imagine a creature the size of a tiger, but with a sprawling, powerful gait and a skull armed with a pair of enormous, saber-like canine teeth. These were the saber-toothed cats of their day, a terrifying and successful group of hunters that sat at the very top of the Permian food chain. The world of Pangaea was the first great age of mammal-like reptiles, a lost world teeming with our own strange and wonderful cousins. The very existence of a supercontinent like Pangaea raises a profound scientific and philosophical mystery. Geologists now know that the Earth assembles and breaks apart its continents in a great, slow rhythm, a supercontinent cycle that takes hundreds of millions of years to complete. What are the deep, convective forces within the Earth's mantle that drive this colossal planetary breathing? And how does this cycle affect the story of life? While Pangaea may have seemed like a mighty unified world, its very unity may have been a source of profound fragility. The extreme climate, with its vast deserts and violent monsoons, created a harsh environment. The interconnectedness of the entire landmass meant there were few isolated refugees, few islands where life could ride out a catastrophe in peace. This leads to a philosophical question about the nature of unity and fragmentation. In our own world, we often see unification as a source of strength, but the story of Pangaea suggests that a unified system can also be a fragile one, susceptible to a single catastrophic point of failure. A world of many separate continents, a fragmented world, might actually be more resilient in the long run. It provides more coastlines, more stable climates, and more isolated laboratories for evolution to experiment. The Permian world was a single grand interconnected empire, but it was an empire built on a knife's edge, a world whose very oneness made it uniquely vulnerable to a global collapse. Let us pause here. In the final years of the Permian, some 252 million years ago, the world has found a new, mature stability. The ecosystems are complex and sophisticated. In the hardy conifer forests of northern Pangaea, a herd of pig-sized herbivores called dicynodonts root through the undergrowth, while a pack of Gorgonopsians watches from the shadows, their saber teeth glinting in the late afternoon sun. This is the golden afternoon of the Paleozoic era. Life, it seems, has finally conquered every challenge the planet has thrown at it. It has survived poison, ice, and suffocation. It has built the most complex and robust terrestrial ecosystem the world has ever seen. The world feels solid, the world feels permanent, but deep beneath the surface of the land, in a part of Pangaea that will one day become Siberia, a vast plume of superheated rock is rising from the boundary of the Earth's core and mantle. An unimaginable pressure is building, preparing to unleash a volcanic cataclysm that will dwarf every eruption in human history. The beautiful, stable world of our Permian cousins is about to face its greatest and final trial. It is about to be baptized in fire. That golden afternoon of the Permian did not last. The peace was a fragile illusion, and the force that would shatter it was not an enemy from the sky, but a traitor from deep within the Earth itself. Deep beneath the Siberian plains, the Great Mantle Plume, a colossal bubble of superheated rock rising from the planet's core, finally reached the crust. The ground began to tremble and split, but this was not the eruption of a single conical volcano. The Earth's crust tore open along vast fissures, some of them hundreds of kilometers long, like immense gaping wounds. From these wounds, there were no explosions of ash, but curtains of fire, roaring fountains of incandescent lava that poured out across the land. This was a flood basalt, a large igneous province, a core scientific concept that represents one of the most violent and destructive geological events a planet can experience. It was not an eruption. It was a hemorrhage. Over the course of the next million years or so, an almost incomprehensible volume of lava, more than 3 million cubic kilometers, would pour out, burying a region of Siberia larger than Western Europe under a blanket of volcanic rock, miles thick. For the creatures living elsewhere on Pangaea, the lava itself was a distant problem. The true killing mechanism was the gas, the planet's own fiery breath released from its lungs. As the lava poured out, it degassed a truly colossal amount of carbon dioxide into the atmosphere. This sudden injection of greenhouse gases triggered a runaway warming event. Global temperatures may have soared by as much as 10 degrees Celsius, turning the already arid interior of Pangaea into an unlivable furnace. But there were other, more insidious poisons. The eruptions also released immense quantities of sulfur dioxide, which reacted with water vapor in the atmosphere to form clouds of sulfuric acid. The rains that fell upon the Permian world were no longer life-giving. They became a corrosive poison. Acid rain would have burned the leaves of the great conifer forests, poisoned the soil, and rendered freshwater lakes and rivers toxic and sterile. And in a terrifying twist, a little-known fact of this event reveals a synergy of destruction that seems almost malevolent in its efficiency. The region of Siberia where the eruptions occurred was a giant basin filled with sediments laid down during the earlier Carboniferous period. Sediments that included the vast coal seams we have spoken of. The immense heat and magma from the eruptions intruded into these coal deposits from below. This effectively cooked the coal on a continental scale and, in many places, ignited it. The Siberian traps were not just a volcanic event. They became the site of the largest natural coal fire in the planet's history. This added a new, even more potent stream of poison into the air. The burning coal released even more carbon dioxide, along with vast quantities of toxic gases like methane and chlorine. It was as if the Earth had not only developed a geological cancer, but that cancer had metastasized into the fossilized remains of its own past life, creating a feedback loop of almost unimaginable destructive power. As the air turned to poison and the planet burned, the oceans, where the vast majority of life still resided, were entering a hell of their own. The assault on the seas was a slow, agonizing death by 1,000 cuts. First, there was the heat. As the planet warmed, the oceans absorbed much of that heat. Warmer water holds less dissolved oxygen, so the seas began, quite literally, to lose their breath. This warming also caused the ocean's circulatory system, the great currents that carry oxygenated water from the surface to the deep, to slow down and become sluggish. The oceans stratified, becoming stagnant. The deep waters, cut off from the surface, became completely anoxic, just as they had in the previous extinctions, but this time driven by a global fever. Then came the acid. The colossal amount of carbon dioxide in the atmosphere began to dissolve into the seawater, reacting with it to form carbonic acid. The very chemistry of the ocean began to change. The water became corrosive. For the countless organisms that built their bodies from calcium carbonate, the corals that built the reefs, the plankton that formed the base of the food chain, the brachiopods and mollusks and sea urchins that carpeted the seafloor, this was a death sentence. Their shells and skeletons, the very homes they had built for themselves, began to dissolve in the acidic water. And in the dark, warm, suffocating depths, a final plague was unleashed. Sulfate-reducing bacteria, which thrive in oxygen-free conditions, began to flourish, producing vast quantities of toxic hydrogen sulfide gas. This gas would have poisoned the deep ocean and may have even bubbled up to the surface and into the atmosphere, delivering yet another killing blow to the creatures on land. Some models suggest the oceans themselves may have turned a sickening, ghostly purple, the color of this toxic bacterial bloom. This was the Great Dying. It was not a single crisis, but a cascade of interlocking catastrophes, an Earth system failure on a total scale. On the land, life was being assaulted by unbearable heat, acid rain, and a poisoned, oxygen-poor atmosphere. In the seas, it was being attacked by heat, suffocation, acidification, and poison. There was no refuge. There was nowhere to hide. It was the most severe extinction event in the entire history of life on our planet. The numbers are almost impossible to comprehend. An estimated 96% of all marine species were wiped out. 70% of all terrestrial vertebrate species vanished. The insects suffered their only mass extinction in their entire history. Life on Earth came so close to being completely and utterly extinguished that the subsequent recovery would take more than 10 million years. The planet almost became a sterile rock once more. The sheer scale of this event forces us to ask a chilling scientific and philosophical question. What, deep within the Earth, is the engine of such profound destruction? What causes these colossal mantle plumes to form and rise? Are they chaotic, unpredictable events, random acts of violence from the planet's deep interior? Or are they part of some great, poorly understood cycle in the Earth's mantle? The Great Dying serves as what some scientists have called a great filter, a challenge so immense that it represents a potential hard limit for the survival of life on any planet. It proves that the planetary system itself can produce a catastrophe so total, so multifaceted, that the usual biological virtues of adaptation and resilience become almost meaningless. It forces us to confront the profound fragility of our existence. We have a bias, a hope, that life is an unstoppable, tenacious force. The Permian-Triassic extinction is the ultimate counter-argument. It is the planet's starkest warning, written in a layer of dead fossils, that life can, in fact, be nearly erased. That the same geological engine that provides the stable ground beneath our feet can, on rare and terrible occasions, become an engine of almost total annihilation. Could it happen again? We can only know that the process that drove the Great Dying is a fundamental part of how our planet works. A slow-motion time bomb ticking deep in the heart of the world. Let us now stand in the silence of the aftermath. The great volcanic fissures have fallen quiet. The planet is a global hothouse, shrouded in a toxic, hazy sky. The oceans are stagnant, acidic, and largely dead. The great conifer forests have been reduced to fields of rotting stumps. The magnificent reefs of the Permian have dissolved into nothing. And our own relatives, the synapsids, the sail-backed predators, the lumbering herbivores, the saber-toothed gorgonopsians who had ruled the world for 60 million years, are gone. Their dynasty has been shattered, with only a few small burrowing species left to inherit a broken world. The silence is deeper and more profound than any that has come before. The great, vibrant, complex world of the Permian is now a ghost world, a planet of ash and whispers. Let us walk now through the world that the great dying left behind. The early years of the Triassic period, which followed the Permian, were an echo, a planetary ghost story. The air is hot and thick and low in oxygen, making every breath a chore. The sun is a hazy, weak disk in a perpetually dusty, yellow-brown sky. The land is a panorama of desolation. The great Permian forests are gone, replaced by skeletal petrified stumps, half buried in red, eroded soil. There is no bird song, no complex insect buzz, only a profound and unnerving silence, broken by the sigh of the wind across vast, empty plains. The rivers are not clear and meandering. They are choked with sediment, a thick slurry of mud and sand washed down from a landscape that has lost its living anchor of plant roots. They are what geologists call braided streams, constantly shifting, impermanent scars on a broken land. This is not a world of life, but a world recovering from a near-death experience. In the rock layers that mark the boundary between the Permian and the Triassic, geologists find one of the strangest and most unsettling pieces of evidence in our planet's history. For millions of years in the Permian layers, the rock is rich with the fossilized pollen of a huge diversity of plants. Then, at the boundary, the pollen vanishes. It is a pollen gap, a moment of botanical death. And in its place, for a brief but ecologically profound period of perhaps a few 100,000 years, the rock becomes overwhelmingly dominated by one thing: the fossilized spores of fungi. This is the little-known fungal spike, a silent testament to a world that was, for a time, given over to rot. Imagine the entire planet, from the equator to the poles, shrouded in a blanket of mold and mildew. This was the kingdom of fungi. Their global bloom was a feast upon the corpse of the Permian world. The trillions of dead trees and unburied bodies of animals were their inheritance, and they became, for a brief dark chapter, the dominant form of life on land. This is the core scientific concept of a post-extinction world. It is the age of disaster taxa. These are not the complex specialized creatures of a mature ecosystem, but the hardy opportunistic generalists, the weeds of the biological world, who were able to survive and thrive in the chaos. On land, the fungal kingdom was the ultimate disaster taxon, the great decomposer. The first plants to return were not mighty conifers, but small, tough, weedy ferns that could eke out a living in the poisoned, eroded soil. In the seas, the same grim pattern held. The intricate reef ecosystems, with their thousands of interdependent species, were gone. In their place, the shallow sea floor was often carpeted with immense colonies of just one or two species of incredibly hardy, oxygen-tolerant clams, like the bivalve chloria. It was a world of profound monotony, where once there was a vibrant, diverse coral city, now there was only a pavement of identical shells stretching for thousands of kilometers. Life had survived, but it had lost all of its texture, all of its complexity. This leads to one of the most enduring mysteries of the Great Dying. Why was the recovery so punishingly slow? After other mass extinctions, life tended to rebound with explosive creativity, filling the empty world with new forms. But the recovery from the Permian-Triassic extinction was different. It took nearly 10 million years for complex ecosystems like forests and reefs to begin to re-establish themselves. For 10 million years, the planet remained a broken, hostile, disaster world. Scientists still debate the reasons for this long delay. One theory is that the extinction was simply too profound. It didn't just prune the tree of life, it cut it down to a stump, wiping out so many key lineages that the genetic and ecological raw material for rebuilding was almost entirely lost. Another compelling theory is that the killing mechanisms did not simply stop. The apocalypse was not a single event, but a new hostile state of being. The Siberian traps may have continued to erupt in pulses for millions of years. The planet's carbon cycle was so fundamentally broken that the world was plagued by recurring hyperthermal events, sudden, vicious heat waves, and repeated pulses of ocean anoxia. Life could not recover because the world remained actively hostile to it. The apocalypse didn't end. It just sputtered and echoed for millions of years, a constant, grinding pressure that prevented any meaningful recovery. Let us try, for a moment, to imagine what it was like to be a survivor. Let us step into the mind of the most famous survivor of the Great Dying, a creature called Lystrosaurus. It was a synapsid, one of our distant cousins, a squat, pig-sized herbivore with a beaked face and two small tusks. It was a humble, unassuming creature, but it was a master of survival, likely because it was a burrower, able to escape the worst of the heat and bad air underground. In the earliest Triassic, Lystrosaurus was astoundingly successful. For a time, its fossils account for as many as 90% of all terrestrial vertebrates on the planet. Imagine a world like that. A world where almost every animal you encounter is just a different version of yourself. A world without predators, without variety, without complexity. It must have been a world of profound, almost existential loneliness. A world of ghosts, where every barren hillside was a reminder of a richer, more vibrant past. This is the deepest philosophical lesson of the Great Dying. It brings us face to face with the razor's edge of existence. Life on this planet came so very close to being extinguished forever. Every single living thing on Earth today, every tree, every insect, every bird in the sky, every human being, is a direct descendant of the tiny, desperate handful of species that made it through that planetary cataclysm. Our own lineage, the small burrowing shrew-like cynodonts that were among the few synapsids to survive, endured. Our existence is an inheritance from those tenacious, terrified survivors of a world of ash. It forces us to confront the sheer contingency of our being. A single prolonged geological event almost erased 3 billion years of evolutionary progress. Life is not a given. It is not an inevitability. It is a fragile, flickering flame in the immense darkness of cosmic time, a flame that has, against all odds, been passed down through unimaginable catastrophes, a flame that has simply refused to go out. The ghost world of the early Triassic did not last forever. The silence was, eventually, broken by the stirrings of new life. After millions of years of stagnation, the planet's systems began, slowly, to heal. The disaster taxa, the clams and the weeds, began to recede as more complex organisms found a foothold. And in the great ecological vacuum, left by the near-total annihilation of the synapsids, a new group of reptiles, the archosaurs, or ruling lizards, began to experiment and diversify. They were small at first, scurrying lizard-like creatures, keeping to the shadows. But they were adaptable, and they had inherited a world with almost no competition. Among their ranks were the ancestors of crocodiles, the ancestors of the flying pterosaurs, and the ancestors of a new and remarkable lineage that was about to rise from the ashes of the Permian and define the next great era of life on Earth. The kingdom of fungi and ghosts was the crucible, the harsh and unforgiving forge in which the first dinosaurs were being shaped. Out of the desolate, silent world of the early Triassic, a new dynasty was born. The archosaurs, the ruling lizards, diversified in the great emptiness left by the great dying. Among them, one particular group, the dinosaurs, began their slow ascent. The Triassic period was their crucible. The Jurassic was their coronation. As the supercontinent of Pangaea began to rift apart, creating new seas and gentler, lusher climates, the dinosaurs rose to titanic sizes. This was the age of the giant, long-necked sauropods, creatures like Brachiosaurus, whose heads towered above the treetops, and the armored Stegosaurus, with the great plates on its back and the fearsome spikes on its tail. For 100 million years they flourished, spreading to every corner of the globe. And this brings us to the final chapter of their reign, the last great period of the Mesozoic era, the Cretaceous. We arrive now at the very end of this period, some 66 million years ago. The world of the dinosaurs is ancient, mature, and at the absolute zenith of its glory. This is the last golden afternoon of the giants. The world they inhabit is a greenhouse. It is a planet of almost unimaginable warmth and vitality. There are no polar ice caps. Lush, temperate forests grow in Antarctica and within the Arctic Circle. The continents have continued to drift apart and are now in an arrangement that is tantalizingly familiar to our modern eyes. A great inland sea runs down the middle of North America, and the oceans of the world are teeming with life. But the greatest change, the core scientific concept that defines this era, is a revolution in the plant kingdom. The world is now in bloom. For the first time, the landscape is decorated with the color and scent of flowering plants. The angiosperms, as we call them, have arrived, and they have transformed the planet. Imagine the first magnolias, water lilies, and sycamores, adding a new layer of beauty and complexity to the ancient forests of ferns and conifers. This botanical revolution sparked a beautiful and intricate co-evolutionary dance. As the plants evolved flowers to attract pollinators, the insects evolved in response. The first true bees and butterflies appeared in the Cretaceous, developing specialized bodies to gather nectar and transfer pollen. This symbiotic partnership, this intimate relationship between plant and pollinator, drove an explosion of diversity in both groups. The world was now filled with new colors, new scents, and new sounds. It was an ecosystem that was, for the first time, beginning to look and feel recognizably modern. It was into this vibrant, flowering world that the last and greatest of the dinosaurs were born. Let us spend a single peaceful day in this world, in the place we now call the Hell Creek Formation of North America. The morning sun filters through the leaves of strange, broad-leafed trees. A herd of triceratops, magnificent three-horned animals the size of elephants, moves through the undergrowth. Their great, bony neck frills, perhaps brightly colored, offer protection as they use their powerful, beaked mouths to browse on low-growing ferns and shrubs. They are social animals, moving in herds, the great adults forming a protective circle around the young. In a sun-drenched clearing, a lone Alamosaurus, one of the last of the titanosaurs, the final generation of the giant, long-necked sauropods, placidly strips leaves from the canopy, its immense body a walking mountain of flesh and bone, and in the shadows of the ferns, tiny shrew-like mammals, our own ancestors, scurry through the leaf litter, largely nocturnal, but perhaps peeking out to witness the passing of the giants who rule their world. As the afternoon wears on, a large herd of Edmontosaurus, a type of duck-billed hadrosaur, makes its way along the bank of a wide, slow-moving river. And among them is another stranger creature, a hadrosaur called Parasaurolophus. From the back of its head extends a long, hollow, bony crest, like the curved horn of some fantastic musical instrument. And that, in a little-known and wonderful scientific fact, is precisely what it may have been. For decades, scientists puzzled over the function of this bizarre crest, but with modern technology, We have been able to CT scan their fossilized skulls and use computer models to simulate the passage of air through them. The results are astonishing. These crests were resonating chambers. By exhaling through them, Parasaurolophus could have produced deep, powerful, low-frequency calls, like the sound of a trombone echoing through the primeval forest. The world of the dinosaurs was not a silent one. It was filled with these deep, haunting calls, a complex language of sound used to communicate across vast distances, to warn of danger, or to call to a mate. It was the planet's first great symphony. As evening begins to fall, the undisputed king of this world makes his appearance. A Tyrannosaurus rex steps out from the tree line. We often imagine this creature as a roaring, mindless monster, but the reality was likely far more complex. It was the product of 100 million years of predatory evolution, a highly sophisticated animal. Its sense of smell was among the most powerful of any creature that has ever lived. Its vision was sharp and forward-facing, granting it excellent depth perception. And its bone-crushing bite was the strongest of any land animal in Earth's history. Fossil evidence suggests they may have been social animals, perhaps even living and hunting in small family groups. The tyrant lizard was a complex and successful creature, the pinnacle of the dinosaurian dynasty. And this brings us to one of the most profound and ultimately unsolved mysteries of this lost world: the nature of dinosaurian intelligence. What was it like to be a dinosaur? We can measure the size of their brain cases, and we know that some, like the small bird-like carnivore Troodon, had brains that were surprisingly large for their body size. We see tantalizing ghosts of complex behavior in the fossil record. Vast nesting grounds that suggest communal parenting, trackways that show complex herd structures, and the intricate crests and frills that hint at sophisticated social signaling. But their minds, their consciousness, are forever lost to us. This forces us to ask a deep philosophical question: what form can intelligence take? We are so accustomed to our own human, tool-using, problem-solving intelligence that we often fail to imagine other kinds. Could the dinosaurs have possessed a different, but equally valid form of intelligence? A deep, instinctual, social awareness. A consciousness woven from scent and low-frequency sound and the complex rhythms of herd life. We can study their bones, but we can never truly know their inner world. They are a great, lost kingdom of consciousness, a reminder that the past is a place we can visit, but never truly understand. Let us pull our perspective back now, high above this peaceful, functioning world. The sun is setting on the last day of the Cretaceous period. A Triceratops settles down with its young. The haunting call of a Parasaurolophus echoes one last time across a river valley. A Tyrannosaurus rex surveys its domain. The dinosaurs are at the absolute peak of their power. They have survived for over 150 million years and reigned so long it makes all of human history seem like the blink of an eye. They are diverse, they are adaptable, and they have conquered every continent. From their perspective, there is no reason to believe their world is anything but eternal. But far out in the blackness of space, beyond the orbit of the moon, a silent traveler is approaching. It is an asteroid, or perhaps a comet, a single piece of rock and ice, about 10 kilometers wide. It has been traveling on its orbital path for billions of years, a leftover piece of the solar system's construction. Now, by a terrible coincidence of celestial mechanics, its path is about to intersect with the Earth. It is cold, it is dark, and it is moving at a speed of tens of thousands of kilometers per hour. It is completely invisible to the creatures of the world it is about to shatter. The golden afternoon is over. The long night is about to fall, delivered from a silent, uncaring sky. The final moments of the Cretaceous period were silent and serene. And then the sky began to fall. From the ground, it would have first appeared as a new star, a pinprick of light, brighter than any other in the sky. But it would not have twinkled. It would have grown, second by second, from a star into a sun, a searing point of incandescent brilliance, burning its way through the atmosphere with terrifying speed. There would have been no sound at first, as it was moving far faster than the speed of sound. There was only the terrible growing light. And then, in a shallow sea off the coast of what is now the Yucatan Peninsula of Mexico, in a place called Chicxulub, the light touched the world, and the day ended. The core scientific concept of a hypervelocity impact is almost beyond our human scale of comprehension. It is not a collision in the way we understand it. The kinetic energy of the 10-kilometer-wide asteroid was so immense, equivalent to billions of the largest nuclear weapons ever created, that the moment of impact was an act of mutual annihilation. The asteroid and the bedrock it struck did not shatter. They vaporized. In a fraction of a second, a crater over 180 kilometers wide and 20 kilometers deep was blasted into the Earth's crust. The solid rock of the planet behaved like liquid, splashing upwards into a transient central peak, taller than Mount Everest, before collapsing back outwards in a ring of molten mountains. The very planet rang like a bell from the force of the blow. From this single point of impact, a wave of synchronized destruction radiated across the globe, unfolding in a series of horrific, cascading steps. First, a colossal curtain of vaporized rock, superheated gas, and molten ejecta was blasted upwards, tearing through the atmosphere and into the vacuum of space. As this material, now consisting of trillions of tiny glassy spherules, was pulled back by gravity, it began to rain down across the entire planet. As these spherules re-entered the atmosphere, friction heated them to incandescence. The sky, all over the world, would have turned a glowing fiery red. This was the thermal pulse. For several hours, the atmosphere itself became a radiant oven, baking the surface of the Earth with a wave of intense heat. Any animal caught in the open would have been cooked alive. And this global heat pulse ignited the world's forests. Continent-spanning wildfires, far larger than anything human history has ever witnessed, raged across the globe, incinerating the lush, flowering world of the Cretaceous. In the thin layer of rock that marks this moment in time, we find a layer of soot, the final global signature of this planetary firestorm. And here, in a little-known and terrible fact, we find that the universe added a cruel geological twist. The asteroid's aim, by sheer cosmic bad luck, was perfect for maximizing the destruction. The location it struck was not deep ocean or solid granite, but a shallow sea covering a thick platform of limestone and gypsum-rich rock. This was a geological worst-case scenario. Hitting granite would have been catastrophic, but hitting these specific rocks amplified the killing power immensely. The vaporized limestone released a colossal amount of carbon dioxide into the atmosphere, a greenhouse gas that would have long-term warming effects. But the vaporized gypsum was the real killer. Gypsum is calcium sulfate, and vaporizing it blasted a cloud of sulfur aerosols directly into the stratosphere. These tiny sulfur particles are exceptionally effective at reflecting sunlight back into space. The planet's own geology had, in effect, loaded the gun that the asteroid fired, providing the perfect ammunition for a prolonged and devastating global winter. As the fires raged, other horrors were unfolding. The impact in the ocean created a mega tsunami of almost unimaginable scale. A wave perhaps hundreds of meters high radiated outwards from the crater, scouring coastlines clean for thousands of kilometers in every direction. Inland, the very ground shook with the force of the largest earthquake in the planet's history. A seismic shock so powerful it may have triggered volcanic eruptions and earthquakes on the opposite side of the world. And then, as the heat pulse faded and the fires began to die down, the final and most patient killing mechanism took hold. The sky, which had glowed red with heat, now turned to an absolute and impenetrable black. It was filled with the soot from the global wildfires and, more importantly, the long-lasting sun-blocking haze of sulfur aerosols. Sunlight could no longer reach the surface of the Earth. This was the beginning of the impact winter. With the sun gone, photosynthesis stopped, almost overnight. On land and in the sea, the plants and the phytoplankton, the very foundation of almost every food chain on the planet, died. In the oceans, this collapse was swift and total. In the darkness, the entire marine ecosystem unraveled from the bottom up. On land, the surviving herbivores, who had somehow weathered the heat and the fires, now found a world of dead and dying vegetation, and they starved. The carnivores who fed on them soon followed. The world was plunged into a cold, dark, and toxic state that would last for years, perhaps even decades. The great symphony of the Cretaceous had been replaced by a long, silent, and frozen night. This brings us to a final great scientific debate surrounding this event, a mystery that touches on the very nature of history and causality. Was the asteroid the sole killer? Or was it merely the final blow to a world that was already in decline? For hundreds of thousands of years before the impact, another major geological event was in progress on the other side of the planet, in what is now India. Another great flood basalt, the Deccan Traps, had been pouring out lava and gas, stressing the global climate. Was the world of the dinosaurs already suffering from a long-term press extinction from this volcanism? Were ecosystems already weakened by climate change and acid rain? The philosophical question this raises is profound. Do great changes in history happen because of single dramatic, unpredictable events? A great man theory of history applied to geology? Or are they the result of long, slow, grinding processes that weaken a system until it is ready to collapse? The end of the Cretaceous appears to be a tragic confluence of both. A world that may have already been sick, suffering from the long-term press of the Deccan volcanoes, was suddenly and violently struck by the ultimate catastrophic pulse from the sky. It was the worst of all possible worlds, a 1-2 punch from the planet below and the heavens above, and so the giants fell. The world that had been their kingdom for 150 million years was gone. It had been burned, battered, drowned, and then frozen in a perpetual darkness. The Tyrannosaurus, the Triceratops, the great Titanosaurs, the duck-billed hadrosaurs with their haunting calls, all were gone, erased from the book of life in a geological instant. With them went the great marine reptiles, the mosasaurs and plesiosaurs, and the flying pterosaurs that had ruled the skies. Their reign, which had seemed so eternal, so unshakable, was over. The silence that fell on the planet was the silence of their extinction. But it was not the silence of total death. In the darkness and the cold, hiding in deep burrows, in freshwater streams, in the leaf litter of the ruined world, small, unassuming creatures were holding on. They survived on the scraps of a dead world, insects, fungi, rotting roots, and among them were our own ancestors, the small, furry, warm-blooded mammals. They had lived for millions of years in the shadows of the giants. Now they had inherited a world of ash and ruin, but they had inherited it. The age of the great reptiles was over. A new age was about to begin. We stand now in the quiet ruins of a fallen kingdom. The impact winter was a world of ghosts and whispers, a long, cold twilight that held the planet for years. In this dim, freezing world, the old rules of survival were inverted. It was not the strong, the large, or the powerful that endured. The giants were the first to fall, their massive bodies demanding a constant supply of food from a world that had become a barren pantry. Survival belonged to the small, the humble, the resourceful. It belonged to the creatures that could hide from the cold in burrows deep within the wounded earth. It belonged to the semi-aquatic life in rivers and lakes, whose ecosystems, based on detritus and rotting matter, were more resilient than the shattered food chains of the land and sea. It belonged to the generalists, the creatures that could eat anything: insects, fungi, roots, the carrion of the dead. And among these scrappy, desperate survivors were our ancestors, the small nocturnal mammals who had spent 150 million years learning to live in the margins, to thrive in the world's dark corners. Their time of hiding was over, as the dust and the aerosols slowly, over years, began to settle out of the stratosphere. A weak, anemic sunlight returned to the Earth. And as it did, we see in the fossil record a remarkable and little-known botanical event. Just as the end of the Permian was marked by a fungal spike, the beginning of the new era, the Paleocene, is marked by a fern spike. The first plants to recolonize the scorched, ash-covered continents were not the mighty flowering trees, but the humble, opportunistic ferns. They are often the first pioneers on any disturbed landscape, and in the wake of the apocalypse, they inherited the earth. For a time, much of the world was a monotonous, silent, green carpet, a global prairie of ferns stretching across the ruins of the dinosaurs' world. An empty world, however, is a world of breathtaking opportunity. And this is the core scientific concept that explains the next chapter of life's story: adaptive radiation. For 150 million years, the dinosaurs had occupied nearly every terrestrial ecological niche for an animal larger than a briefcase. They were the dominant large herbivores, the dominant large carnivores, the dominant medium-sized everything. Their sheer success had suppressed the evolution of the mammals, keeping them small and constrained. Now all those roles were suddenly, catastrophically, vacant. The stage was empty, and the mammalian survivors were the only actors left. Imagine a vast ancient library where a fire has burned all the great classic volumes from the shelves. All that remains are a few small, overlooked pamphlets, but the shelves are empty and waiting, and so those pamphlets are copied, expanded upon, edited, and elaborated until they have blossomed into thousands of new, rich, and varied volumes, filling the entire library once more. The mammals were those pamphlets, and they were about to rewrite the book of life. In the first few million years of the Paleocene, the survivors began to radiate, to experiment with new forms to fill the empty niches. The mammals, which for their entire previous history had been no larger than a badger, began to grow. The first large lumbering herbivores and clumsy archaic carnivores appeared, evolving in a world without predators to fear. As the Paleocene gave way to the Eocene, the climate, after the initial impact winter, swung to the other extreme, becoming a sweltering global hothouse, and this warmth seemed to fuel the mammalian explosion. This was the true dawn of the age of mammals. The first ancestors of horses, no bigger than a dog, were running through the humid subtropical forests. The first primates, our own order, were leaping in the trees. The first bats were taking to the night sky, and in the seas, the first whales descended from hoofed land mammals were returning to the water, the home their distant ancestors had left so long ago. And they were not alone. The birds, who we must remember are the last surviving lineage of the dinosaurs, underwent their own explosive adaptive radiation, filling the skies with a new diversity that would eventually outnumber the mammals. And this brings us to our final and perhaps most profound unanswered mystery: the question of contingency. Our journey through these 5 great endings has shown us that the path of life is not a straight, predictable road. It is a winding, chaotic, and unpredictable trail, punctuated by catastrophic interruptions. And this final interruption, the stone from the sky, raises the ultimate philosophical question. A thought experiment, famously proposed by the scientist Stephen Jay Gould. If you could rewind the tape of life to that golden afternoon of the Cretaceous and play it again, would the result be the same? If the asteroid had missed, if its orbit had been shifted by the gravitational nudge of Jupiter just a few thousand years earlier, what would the world look like today? Would the dinosaurs have continued their stable, successful reign? Would a species of intelligent dinosauroid, evolved from a large-brained carnivore like Troodon, be contemplating the stars tonight? The answer, written in the story of the KPG extinction, is almost certainly no. The outcome was not inevitable. The rise of mammals and the eventual much later evolution of human beings was not the grand final act of a pre-written play. It was the result of a cosmic accident, a lucky break of unimaginable proportions. We are the children of contingency. Our existence is owed to a random event that wiped out a more successful, more dominant, and far more ancient dynasty. This is not a thought that should make us arrogant, but one that should fill us with a deep and profound sense of humility and of wonder. Our place in this universe is not one of entitlement. It is one of almost impossible astronomical luck, and so our long journey through time comes to an end. We have stood on the shores of an iron-rich sea and felt the first poisonous breath of oxygen. We have watched a world encased in ice and seen it suffocate in the thaw that followed. We have walked through the first alien forests and witnessed how their very success poisoned the oceans that gave them life. We have stood in the ashes of a world burned by fire from within, the closest life ever came to total annihilation. And we have watched a stone fall from the sky and erase a kingdom, clearing the way, by sheer chance, for our own. The story of our world's great endings is a story of many different kinds of death. But the one common thread that connects them all, the single quiet truth that echoes from every one of these lost worlds, is the simple fact of survival. The thread of life has been stretched, frayed, and nearly broken, time and time again, but it has never, not once, been truly severed. The story of the 5 times the world nearly ended is, in the end, the story of how it always, somehow began again, and now our journey through the deep past is over. The echoes of those lost worlds, of the great endings and the new beginnings, begin to slowly fade. Let the memory of the fire and the ice, of the silent forests and the suffocating seas, gently brush past your awareness, like clouds drifting across a quiet moon. The great story has been told, and all that remains is this moment, right here, right now. Bring your attention back from the vastness of time to the simple, peaceful space that surrounds you. Feel the gentle weight of the blanket on your skin, the soft pressure of the pillow beneath your head. Notice the quiet rhythm of your own breathing, a simple ancient pattern that connects you to the entire story we have just witnessed. The air you are breathing now is a gift from those first cyanobacteria. The strength in your bones is a legacy of the survivors. Your very consciousness is an improbable bloom that grew in the ashes of a fallen world. I'd like to gently ask one last time, where is the place you're staying now? The time in that place, at this very moment, how is it flowing? Feel the quiet anchor of your own small corner of space and time, a safe harbor from the immense, deep oceans of the past. If our journey tonight has brought you some small measure of peace or wonder, perhaps you'll consider sharing it with someone else who might need a quiet story to help them find their own rest. Let the last vestiges of our story dissolve now, leaving behind only a sense of calm and a quiet curiosity. Let your thoughts soften and your body grow heavy with the gentle pull of sleep. Sleep well, my companion, wherever and whenever you are. Sweet dreams.